Right now. Okay, good morning to everyone here in the room and online. We're going to start the third session of Division A days. So welcome. We have 6 presentations, 1 invited and the remaining contributed. And of course, you can, at the end of each one, make questions, suggestions, comments here, but also online by voice or via the chat. The first talk is by Ivesic about Rubin's LSST as an astrometric and photometric survey, and he has 30 minutes, so please.
Good morning. Let me start by thanking organizers for inviting Rubin Observatory to present this. There we go. So Rubin Observatory is a new observatory that is about to be finished. We will begin with operations next year. And it has 4 main science teams that were used to optimize observations for so-called legacy survey of space and time, LSST. But just by itself, the way data will be obtained, it will also be a very general astrometric and photometric survey. And so I have 2 slides that speak to details of that astrometric and photometric survey. But in order to put it in context, I have some more slides to talk about the observatory in general. So I'll give you a brief introduction, assuming that not everyone is deeply familiar with the observatory and LSST. I'll spend a few slides telling you where we are and why I believe that we will be done next year and begin the survey. And then I'll give a few very detailed slides about properties of this astrometric and photometric survey. So compared to other great observatories that are being built or that are already in orbit like JWST, Rubin is not especially large primary mirror. It's only 8.4 meters, which pales compared to these other upcoming telescopes. But it is special because it has the largest field of view. It has field of view 100 times larger than typical 8 to 10 meters telescopes. And that is why it can scan the sky. It's a survey instrument. It can scan the sky 100 times faster than any other comparable telescope. So we think that we can deliver LSST in 10 years. You could do it with other telescopes, for example, Gemini South or North, but then it would take you 1,000 years. So that huge difference is due to big field of view. This is Vera Rubin, famous for dark matter, famous for improving work conditions for women in astronomy. So the observatory was named after her. Here is visual. So this is another public telescope, public US telescope, Gemini South, which is actually our neighbor, only a few hundred meters from our site in Chile. And you can see in the upper right, field of view for Gemini. It's 0.2 degrees across, but Rubin field of view is 3.5 degrees across, 10 square degrees, and that is why we can scan very fast. Of course, such a large field of view with Nyquist sampled atmospheric seeing leads you to many gigapixels. Indeed, we have 3.2 gigapixels in focal plane, and so then that requires exquisite software, data processing flow, etc. We will be using filter set that is very similar to SDSS. Indeed, the only significant difference is that the SDSS Z band on the right was split into 2 bands that we still call Z, the red one, and purple is Y. That was done to improve sensitivity for very high redshift quasars and other objects to push it out to redshift of about 7 or so. But bluer bands will have similar performance as SDSS, in particular for star quasar separation and for determination of stellar photometric metallicities. There will be no time allocation committee. The observations will be scheduled using cost-benefit function, computed in advance at the beginning of night, and then adjusted if needed due to weather. Every 40 seconds, we will acquire a new 10 square degree field. Sometimes about 10 to 15 times per night, we will change filter. We have 5 filters in the camera out of 6. So once a month, we may change to U or to Y. And so this basically illustrates how we would observe the sky. The data will be very deep. So each observation, that 30-second exposure time, will be 3 magnitudes deeper than SDSS. And when we co-add hundreds of observations at the end of the survey, we will achieve 5 magnitudes deeper images, or factor of 100 in flux. This is SDSS images, color composite GRI, 1/10 of moon's diameter. So it's teeny tiny on the sky. And so this goes down to 22nd magnitude. When you go 5 magnitudes deeper, this is next slide, and we already have it because we obtained that image from the Japanese Subaru telescope, which cannot go across the whole sky as quickly as Rubin, but it can certainly achieve the same depth over the smaller field of view. So this is how it looks like. So that's the real sky, that's not simulation, real same position on the sky. This is what happens when you go 5 magnitudes deeper. Whenever I get tired of Zoom telecons, when I get tired of work, I go back to these 2 slides and then flip back and forth to give myself more motivation. It's beautiful. And so you see how we go deeper, we get many more objects. So that is the main reason why we will have about 20 billion with B galaxies in the sample and a similar number of stars, close to 40 billion objects. And each of these objects will be observed close to 1,000 times over 10 years. And that's why it will be the greatest ever astrometric and photometric survey that we collected as astronomers. So it's not only obtaining the data that we plan for, but we will process these images first, of course, to calibrate them properly astrometrically, photometrically. And then our software pipelines will detect objects and measure their properties. So regular static data releases will happen once a year, but we'll also have real-time processing to catch changing objects, either in flux or position. And that information will be reported to everyone in the world without restriction within 60 seconds. So our software team is fairly large, close to 100 people. It's interesting that software effort costs as much as the camera itself or the telescope and observatory. It's over $100 million effort for each. So here is illustration of what that alert production pipeline will do. It will take 2 images, subtract them, like in the first row. If nothing changed, you'll get sky background noise. That's basically how Tombaugh discovered Pluto, except we will now do it with computers. In the bottom example, there is a new object, and it shows as black because it's 1 minus 2. And that is what we call alert. Any object detected in different images is called alert. We expect about 10,000 per each observation. With about 1,000 observations per night, we expect up to 10 million such alerts per night, or 300 billion in 10 years. So let me quickly tell you about the status of construction. The top row shows computer-generated design that is about 15 years old. And the bottom row are actual photographs of the hardware produced according to the design. So the bottom row is the real stuff. On the left is the observatory, in the middle is telescope, on the right is LSST camera. Telescope is very short and agile. This is real time. This is not sped up in video. This is how fast it can move. In 20 seconds, we can turn from one direction of the sky to the opposite. Typically, it will take about 6 seconds to slew from one field to the other to stabilize and begin the new exposure. It's quite impressive to observe it in real time. It's really large and looks massive, but then when it starts moving, it draws 1 megawatt of power. Of course, we don't have lines that bring 1 megawatt of power, so we have giant capacitor banks. So you can think of it as robotic battery-operated telescope. This is the camera. It's already in the Guinness Book of Records as the largest astronomical camera ever made. It's as big as SUV. It's Nyquist sampled atmospheric seeing across 10 square degree field of view that led to 3,200 megapixels. On the right, you can see the results of electro-optical testing. Each CCD, each small square is one 4K by 4K CCD that has 16 readout segments, each with their own amplifier. So there are 3,000 something amplifiers in the focal plane. All but 3 work, 99.9% are operational. The readout time is 2.4 seconds because there are 16 segments. So it's 3 gigapixels read at 500 kilohertz in 2.4 seconds. On the left, you see this camera as of 2 months ago, when it finally arrived from California, from SLAC laboratory, where it was assembled, to the summit in Chile at Cerro Pachon. Now it's in clean room, and we are now cooling it down, and we'll repeat measurements like this to establish that nothing changed during transport by airplane from San Francisco to Santiago. So this is summary of what's left for us. So we are just about, last week we put M2 secondary mirror on the telescope. This week we will put commissioning camera that looks just like the one you saw from the outside, but inside has only 9 CCDs, not 189. Then in few weeks, we'll put primary tertiary mirror in the telescope. We expect first on-sky images in September, sometime in September. We'll do that for about 2 months. By that time, big camera will be ready to go on the telescope. So in December, we'll put big camera on the telescope. Sometime in January or February of the next calendar year, we will have first on-sky images with the big camera. Then we'll do 2 months of science validation, essentially LSST-like survey. And sometime next summer, we expect to be essentially done with construction. And then we'll switch to operations mode, when Rubin Observatory will become one of the units of the new US National Observatory called NOIR Lab. It used to be NIAO. I think I saw Dave Silva somewhere in the room, or he left. He was former director of NIAO. So it's now NOIR Lab, and Rubin will be operated by NOIR Lab and SLAC. It will be lots of data, 300 petabytes. So the question now is, how will you get to that photometry? You will not download it on your laptop at home. So we are also developing quite exquisite set of tools that we call Rubin Science Platform that will allow you to download a little bit of data if you want to, but also if you want to process the whole data set, if you want to look for some peculiar objects among those 40 billion objects, you do not have to download data. You can upload your code. You can program IPython notebooks and do your science in situ on our data system. So you can also do other ways of accessing. I will just emphasize notebooks. Portal is when you actually do it in real time. You can look at individual objects that you may like. But if you want to do massive statistical analysis, you will be using notebooks or sometimes even APIs if you have more compute power at your disposal. We already have lots of documentation. This is entry point, where each of these links on the left are quite exquisite examples. They are notebooks written in Python that show you, that tell you, teach you how to access data and analyze the data. There is a lot of documentation. We already have quite exquisite operations team. So basically, we are both in construction and in operations. There is also operations team that is gearing up to start operations next year. Here are a few examples. So you have to learn Python. Sorry, no Fortran, no BASIC. You have to learn Python. If you're old and don't know Python, like I didn't, if you want to survive, you have to learn Python or find grad student. So basically, you can do whatever you want without downloading the data. That's the key message. You can look at images. You can ask how many times my object was observed in this part of the sky. There are also, I removed that slide, there are plotting tools that are intelligent enough that if you give it sample of billion objects, for example, it will not choke. It will not die like Microsoft products. It will basically, I'm from Seattle, I can say that. It will basically dynamically rescale, readjust, use contour diagram where there are too many objects. If there are few, if it's sparse, it will actually use symbols. It will be tool that will allow you to easily work with billions of objects. So what about astrometry and photometry? As I said, it will be the largest set of astrometric and photometric measurements ever produced in astronomy. We will have about, let's say, for the ease of calculation, 10 billion objects, and each will be observed about 1,000 times. So it will be 10 trillion photometric measurements and 10 trillion astrometric measurements. Like with astrometric measurements or photometric measurements obtained by Gaia, this will be about 100 times larger data set. And so Gaia is one of gold standards right now. So this diagram is a good one to illustrate how will LSST astrometry and photometry compare to what Gaia delivered. So Gaia, of course, is space-based survey. So they can do so precise measurements that you'll never be able to obtain from the ground due to systematics induced by the atmosphere. So if you look at the top diagram, that's photometry. So it shows with two red lines what is photometric precision of Gaia measurements. One measurement, n equal 1, gives you 1 millimag, which increases to about 10 millimags, 1%, 0.01 magnitude, at the limit of Gaia at about 20th magnitude. One measurement from LSST has flat bright part. This is systematic dominated atmospheric systematics, about 5 millimags photometry. And then again, it increases towards faint end due to photon statistics. But it goes much deeper than Gaia. So if you look at Gaia and LSST together, it's almost like intelligent design, almost like we said, let's do what we can from space and the rest we'll do from the ground. Of course, they were independent missions, but from the astronomical point of view, they will be great complement for each other. And then also for proper motion and parallax, you can see in the other two panels that Gaia and LSST will be highly complementary. And so we will use Gaia to exquisitely calibrate LSST astrometric and photometric measurements. But then with LSST, we'll go in with photometry, with static photometry and astrometry, we'll go about 5 magnitudes deeper. And for time domain, if you want to measure proper motions, if you want to get light curves for variable stars, that will go about 3 magnitudes deeper than Gaia. And so why are we so confident that we will deliver? We already have data sets from other cameras, like dark energy camera, like HSC on the Subaru telescope, that are being processed with our software pipelines. And we already have exquisite QA tools that tell us how we are doing. So here are a few plots from Eli Rykov from SLAC, who is our photometric calibration scientist, where he recalibrated the dark energy survey data using method that they call forward global calibration method, FGCM, that was pioneered by SDSS survey, who called it Eber calibration, where basically you use all the observations you have, multiple observations, to also fit for systematics in your instrument and then get the best possible calibration. The point here is that they managed to calibrate broadband photometric data from the dark energy survey to within few millimags relative to Gaia. Indeed, in the right panel, you can see Gaia scans on the sky. So Gaia isn't perfect either. It's a fantastic survey, but it's not perfect. It has its own systematics, and you can tease them out if you have enough even ground-based data. Here is another test pioneered by SDSS where you ask, how narrow is the stellar locus? So with broadband filters, stellar colors depend on effective temperature, metallicity, and log G. So it's 3-dimensional space, but in projections, it looks like 2-dimensional ribbon. And then if you look at the right projection, you have essentially zero width locus, like few millimags. And so if your errors are more than few millimags, then the width of stellar locus will give you independent measure of how well you are doing. And that's what Eli did with these diagrams and demonstrated that our software can model the point spread function from HSC and dark energy survey. These plots are from HSC, and obtain precision that we require for LSST, which will be 5 millimag repeatability systematics. You may have heard that we will have 2 different types of CCDs in LSST camera because we couldn't procure all 189 from the same vendor. They are similar but not identical. And so people who are in love with photometric precision or astrometric precision often ask, but how are you going to calibrate two different sensors? And the answer is it will not be a big deal because difference between them is smaller than differences in effective bandpass induced by moving from zenith of 1 to zenith of 1.5 or so, which is our upper limit. So we already have to have exquisite calibration to account for different air mass, and differences between our sensors have smaller effects than that. So I will leave a few minutes for questions. I will conclude with this slide. So things to take home are billions, tens of billions of objects observed up to 1,000 times over 10 years. And if you want to learn more details, in the top right, there is short URL, ls.st/LOP, LSST overview paper, where you can find many more details about the surveys, about the science we want to do, as well as links to much more material than I could fit in these 20 minutes. Thank you.
Thank you very much. We have time for some question or comment.
That 2, 3.
Wait for the microphone. Any problems with the large amount of artificial satellites planned to be launched, which might be pretty bright?
Yeah, short answer is it's nuisance that we have to address. We already developed software for finding tracks in images, masking them. Eventually, we'll also fit the profile. We think that close to 80% of fields will have one track in the field. For twilight fields, we are certain that all the fields will have one track on average, assuming 50,000 satellites. Now, our field is very large. So if you take 1 arc-minute thick mask, then you get very tiny fraction of pixels that you lose, even though it looks super bad when you display it on computer. So the bottom line is we think it will be fraction of percent, not quite 1% of pixels that will be affected by satellites. If they will have 50,000 satellite constellations, but there are already requests filed for 1 million satellites. And if they will be not much brighter than 6th or 7th magnitude, but if you look at Blue Walker, it's as big as this room, and it's like 0th magnitude. So at this moment, based on what we know, it will be nuisance, not catastrophic. But we cannot exclude the possibility that the grid will lead to catastrophic failures for astronomy.
Thanks for that great overview, Joko. So I'll give you a comment here, a comment and a question. So the Roman Space Telescope is a similar science platform, as I'm sure you know. And I thought it was really interesting at a recent conference where we baited both of these things and realized how similar both science platforms were. But it got me wondering, how much are you thinking of letting people bring their own data into the Roman or the Rubin Science platform?
Yeah, we are budgeting for about 10% of capacity, 10% in both volume and CPU. Now, that may be sufficient for many usages. For example, Gaia catalog in this context is tiny. But to bring Roman images, that will not be tiny. So indeed, there is an independent effort that is trying to develop groups that will develop software that will simultaneously process Rubin and Roman images, because Roman brings in higher angular resolution and also extends wavelength range. So together it will be powerful synergy, but you have to extend at least Rubin software to be able to do that. So it is a major effort that people are planning for.
Hi, Dave Tholen, University of Hawaii. One thing that hasn't been clear to me during the development of Rubin is how much time is going to be spent looking at small solar elongations, which is a rich hunting ground for near-Earth asteroids that hide from opposition surveys.
Right now, we will use pretty much all of the twilight observations for that. It's about 5% of the total. It is not 5% of the dark time, but it's significant, and it was improved greatly over last year with the new simulations, cadence simulations that we have. So that is all available already on the web publicly. So you have a list of all the observations, so you can look yourself, but there are also metrics that are automatically computed that were designed by Lynn Jones and her group. She is solar system astronomer, that will tell you immediately how many observations are that many degrees from the sun. We actually will be sensitive even to objects within the orbit of Venus, not only between Venus and Earth, but within orbit of Venus. And if you looked at National Academy of Science recent reports, they have even figures that include Rubin and that show that you can only observe tangentially to Earth's orbit, implying that we would not see a single object that is closer to Sun than orbit of Earth, which of course is wrong, but it was also proven as wrong by Zwicky transient facility. There are lots of objects that were discovered over the last couple of years by Zwicky transient facility that demonstrate we will do the same with Rubin, but we will even go deeper and will be more sensitive. Solar system is one of the 4 major science themes that we address.
Hi, thanks. Really exciting opportunities coming up here. Real quick question. So you mentioned that will be an API. Are you intending full operation with like AstroQuery if you want to download your own tiles of interest and things?
Correct, but not the whole data set, of course. Yeah. The whole data set will be just images, 60 petabytes. But if you want to play with everything, we are planning for 500 petabytes at year 10.
And I may also real quick, do you have any plans for like a deep field? Like obviously you'll have wide coverage, but
we do. Just Google LSST deep fields. You'll get the list. There are 6 of them, and they'll have about 10 to 100 times more observations than regular survey.
Fantastic. Thank you.
And if there are questions for the people online, please put them in the chat. Are there other questions here in the room? Let me check the chat again. No. Maybe I would have one, maybe even less related to LSST, but looking at the complementarity between Gaia and LSST, are there any plans or any needs to do similar work in the Northern Hemisphere?
It would be great to have something comparable. At this time, if you wanted to cover the whole sky, then you would probably go and combine with Pan-STARRS and with dark energy survey. Mostly with Pan-STARRS, they do give you down to, I think, 22, 20, even 23. So we are not completely blind in the northern sky, but it's not as deep as LSST will eventually go. Thank you for great questions.
Yeah, thank you. Thank you again.
Okay. Then let's move to the contributed talks. Now about Earth's rotation. The time is about 10 minutes plus 2 minutes for the questions. So next we have Wang with nonlinear terrestrial reference frames and EOP's determination based on singular spectrum analysis.
Okay, thank you.
You have to pass with this, and this is the pointer.
Oh.
This and this to pass, and this is the pointer.
Okay. Good morning. I'm Xia Wang from Shanghai Astronomy Observatory. My topic is nonlinear terrestrial reference frame and EOP determination based on singular spectral analysis. Okay, my talk includes the following 5 parts. The first one is background and significance. As we know, the Earth's rotation, gravity field, and geodynamics are the 3 main research branches of space geodesy, and they are all strongly related to the reference frame. The terrestrial reference frame and EOP are determined together by the following four techniques: GIS, SR, and VRBI, and Doris. The accuracy and the stability of TRF are required to the 1 millimeter and 1 millimeter per year respectively. And the millimeter precise orbit determination and other fields such as space VRBI, integrated PNT, crust deformation monitoring, sea level change monitoring, and space gravitation wave detection all required the high accuracy special temporal reference. How about the present status? We have 3 TRF series, such as ITRF, DTRF, JTRF, and our STRF. They are different in some degree. For example, in the ITRF, seasonal period and post-seismic deformation, PSD models are determined to prove the accuracy. DTRF considers the atmosphere and hydrological tender loading correction. The DPI used the camera filter and the background smooth approach to realize their linear TRF. For us, we introduced a weighting method of various component estimation to obtain a linear TRF firstly, and then continue to analyze the coordinated residue time series to obtain the non-linear TRF and EUP. Before I introduce our method, I want to show the 3 phenomena. We find that there are unlabeled jump in coordinated residue time series of some stations. The position of stations was offset, and the coordinated residue time series showed a significant unlabeled jump. The second phenomena is non-linear motions. There are period motions in space geodesy stations, especially GIS stations. Their amplitude show complex time-varied characteristics. They are related to the geophysical factors such as climate change, groundwater, tender ocean loading, and so on. The third one is post-seismic deformation, PSD. We adopted the ITRF PSD model. Here, I don't introduce it. So I will introduce the station discontinuous detection, time variable signal extraction, and determination of TRF and UP. The second one is station discontinued detection. We adopted the GSD and the STARS to detect the unlabeled jumpers. I don't give these methods in detail. You can see those papers. After we introduce those unlabeled jump into the discontinued information file and calculate the TRF, we find both the jump and the linear trend term are efficiently removed. The mean value and IMS and S are significantly reduced, and the station discontinuous have been repaired very well. Unlabeled jumpers effect on the TRF and EUP. According to the statistics, after introduce the unlabeled jumper, 95% of the stations, the IMS values are reduced, indicate that the accuracy of the solution B result is better than the solution A. Solution B is considered the unlabeled jump. This is the effect on the EUP. We can see the these comparisons of UPWS for the solution A and solution B. We can see the solution B is better than the solution A. About the occlusion, the arms are reduced by this sum. The three part is time varies period signal extractions. We adopt the SE to fit the time varied period single. So before they use apply the SSE, we need to do the data processing because there are always some data missing. So we need to make this data continuous. And we do the little squares fit and SSA. The green one is the original data, and the red one is the fitting by the SSA, and the blue is the least squares fitting. So we can see the red one is better than the blue one. So after applying the SSE result, the period composed at different scales can be identified and extracted as seen in these figures. The arms values are also reduced. Here I show the first part. The first part is determination of a linear terrestrial reference frame and UP. We can see the result of determined definitions. Firstly, here is the translations parameters. We can see the linears and the non-linears is very consistent, but there are still different. You can see the WIMs. After this is the scales, SR scale and the VRBR scale. We can see that after introduce period components and the recalculations, the stability of translations and the scale is improved, but is not obvious, especially the translation parameters. It is because that the period signal extraction and the process are mainly applied in the GS data, which are not used in the determination of datamer definition. Oh, okay, I will quickly. This only shows the GPS result. We can see after the linear STF is better than the linear STF. This is the result. We can see the coordinate occlusions is following these levels. There are 10% GPS stations, only 3% VRBR, and this 0, and this is for the stability. So we can see the TIF occlusion and stability still need to be further improved. This is the UP's result. Also shows they are improved after the non-linear terrestrial reference frame. The UP's data. So conclusion and outline. Those unlabeled examples need to be detected, and the JESD and STAIs are good method for such detection. After you introduce them into the discontinuous file, the TF and UP are recalculated. Both the example and the linear trend term are effectively removed. The mean value and the arms are significantly reduced. Time varied period single extraction by applying the SSA, the period components at different scale can be extracted. The IMS values after remove the period components are reduced. Non-linear TF and UP could be determined after unlabeled examples, times various period single and PSD are improved. So they are those accuracies are all improved. Outlook, besides the above presence on site coordinate time series, we still need to improve the accuracy of space geodesy data presence. Now we have finished the solar radiation flux model update, Earth radiation promotion, and other model. Other factors are still on study, such as multi-passive effects and atmosphere ties. In future, most sites will certify the requirements of GGOS to the TIF. Thank you very much.
Thank you very much. We have time for some quick question or comment, if any, please. The micro, please.
Looking at the chat.
Hello, good morning. I was wondering, what is the geophysical interpretation of a nonlinear model?
Non-linear should just not only concern the coordinate and the velocity and other period signals. You know, the station's movement include many different signals. So we just not only concerned the linear's term, also the non-linear's term. Yes.
Okay. Thank you. We have to move to the next presentation. Then the next presentation is by Yolanta Nastula about gravimetric excitation of polar motion from SLR plus Grace FO hybrid solutions. It works. You have to pass with this and this. This is the pointer, and you can see the time there. Close to the
Moment.
This and this one, right?
Okay. So it is my pleasure to tell you about our results concerning gravimetric excitation of polar motion from SLR plus Grace hybrid solutions. So let me start from introduction. The excitation of polar motion resulting from changes in mass redistribution of the hydrosphere can be expressed with hydrological angular momentum, HAM series, which can be estimated from global models of continental hydrosphere, Earth gravity field variation, and numerical climate models. And the gravity recovery and climate experiment GRACE and GRACE follow-on missions have provided valuable data for estimating the gravimetric excitation in polar motion. The main objective of this study are to compare HAM, so hydrological angular momentum derived from changes in the gravity field as obtained from GRACE follow-on, with the hydrological signal in geodetically observed polar motion excitation, also known as geodetic residuals or GAO. Also evaluate whether the degradation of observation and the end of the GRACE mission and the need to fill data gap between the end of GRACE and beginning of GRACE follow-on using different statistical methods affect the level of agreement between geodesy and HAM, and check whether the use of combined solution from GRACE follow-on and satellite laser ranging could improve the consistency between HAM and GAO. So here we use C21, S21 series of coefficients of geopotential made available by International Center for Global Earth Models. We have 3 sets of grace-only solutions from CSR, JPL, ITSG, and also hybrid solution from EGG and CNES. I would like to say just a few words about this IGGG hybrid solution. They are listed in the table, and there are kind of combination. Changes in gravity are modeled using empirical orthogonal function from GRACE data, with scaling adjusted dynamically in orbit determination. So, and details can be found in this paper. So we have 6 hybrid solution from IGG. Yes, and we use to compute HM very known formula, known equation that describe linear relationship between K1, K2 components of excitation and changes in degree 2 order 1 coefficients of the geopotential. And now, what about geodesy? Hydrological signal in polar motion excitation, GAO, is computed as a difference between geodetic angular momentum obtained from geodetic observation and sum of atmospheric angular momentum and oceanic angular momentum. So the geodetic excitation data are provided by IRS, and to compute this hydrological signal, we use 2 combinations of HAM and AAM and OAM, so you might see here the data. And final signal uses studies just arithmetic mean of these 2 kinds of residuals. And we had to make some pre-processing. So all the data series were interpolated to uniform time step. And we use Gaussian filter, but also due to a nearly 1 year gap in GRACE follow-on data, a specific approach was required. The gap was addressed using the autoregressive integrated moving average method. Our analyses are divided into seasonal and not seasonal variation separately. Seasonal oscillation obtained by fitting the model, sinusoid with period of 4, 6, and 12 months using least square method, and non-seasonal variation obtained by subtracting the trend and seasonal oscillation. And additionally, non-seasonal changes were divided into short-term variation with periods shorter than 600 days and long-term variations. And also, what is important, the correspondence between hydrological angular momentum and GAO for non-seasonal variation are analyzed for 2 periods. Full period between 2002 and 2021, and period of the best GRACE data, best GRACE performance between 2002 and 2014-5. So let's start from non-seasonal variation, short-term and long-term. So this figure displays results, comparison. On the left, amplitude spectra comparison. On the right, time series spectra, starting from GAO, then hybrid solution, and GRACE-only based solution. Well, so one can see some similarities in the spectra, common variations, around 600 days in the retrograde part, also in the prograde part around 300, perhaps it is remaining after incomplete removing of seasonal oscillations. And also we can see some common features in time variations. I should add that time variations are shifted artificially one to another. But I would like point your attention to this part of variations. So it is only in the grace-based data, not in hybrid data, and it is results of deterioration of the GRACE mission data in the end of the mission, and also need of filling gap between GRACE and GRACE follow-on. And it is especially seen in JPL data. And next example of our comparison, long-term variations, again, time series, we may see some common feature, for example, in K2 between 2008-2014 lasting maximum, and what is interesting, around 6 hours, 6 years oscillation in the spectra. And also, it is not surprising that there is no so variability here, like for in short time series, and also there is no evidence of this time of worse quality of the data. And now a more quantitative comparison. On the top, correlation coefficients, and on the bottom, root mean square error. So it is again GAO versus HAM. And we compare here two periods, this shortened one, red bars for the best GRACE data quality, and this full data period, so blue bars. And we can see first that we have pretty nice correlation in the case of hybrid, in the case of in the case of hybrid data here. And we can see that including of this period of worst, not so good data in the end of GRACE mission, lower correlation. So you may compare results, these three first bars on the beginning, yes. Compare red and blue. Now, similar comparison for long-term variation. So here, these correlations are even better, pretty large, like 0.8, and there is no clear impact of this period of disturbances between GRACE and GRACE follow-on. And seasonal oscillation. So we, this figure show comparison of phasor diagrams of annual and semi-annual oscillation. Geodetic data are shown by black vector, but it is difficult from this picture to judge which where is the best agreement. So we just computed differences between GAO and HAM, and we are looking for the smallest one in phase and in amplitude. And it turned out that in the case of phases, again, hybrid solution performs better than GRACE for annual prograde, especially, and also amplitudes in the hybrid solution perform better than GRACE for annual prograde and retrograde terms, respectively. And for semi-annual oscillation, we have mixed results. In the case of phases, the GRACE-only based solution demonstrate the best agreement with GAO for semi-annual prograde, semi-annual retrograde, respectively. And in the case of amplitudes, the hybrid solution is better. Okay, so conclusion. Our findings demonstrate that HAM derived from hybrid solution closely aligned with GAO. They perform similarly or even better than the series derived from GRACE follow-on data. The influence of time period considered either full period of grace and grace follow-on activity or period of best performance is evident, especially for short-term non-seasonal oscillations, but it's not visible for long-term variation. Also, we noted high correlation between GAO and HAM for hybrid solution for long-term non-seasonal variation. And in the case of seasonal oscillation, HAM from hybrid solutions provide higher consistency with GAO than HAM from grace-only solution, except for phases of seminal oscillations. So generally, we have nice agreement between GAO and HAM. Thank you for your attention.
We have time for some question, if any. Cheng-Li.
As we discussed on last Friday, we talked about the contribution of the crystal to the channel wobble, as we want to shoot. And my question is, did you try to separate the polar motion by two parts, like the channel wobble and the others? Because channel wobble is the biggest one. So we can see how the crystal contribution to the other parts of channel of the polar motion. That will be my interest.
Yes, thank you for your question. We have not made this kind of comparison yet. We analyze polar motion excitation functions. So to do this, we need to just compute polar motion xy from excitation function. Yes, but it is a nice idea, of course.
Thank you. Thank you.
Nothing else? Okay, thank you again, Yolanda. The next speaker is Cheng-Li Huang with origins of the intradecadal oscillations in length of day and implications.
Monitor? What?
Yes, and you have the timer there. I will give you some indication.
Thank you. No? Okay. Okay, good morning, dear colleagues and friends. I'm Cheng-Li Huang from Shanghai Astronomical Observatory, and Anshu Duan was my postdoc and is staying in my group now. And my topic today is on the origins of the sub-decade oscillations in length of day and its possible implications for us to study the Earth's interior. Okay. Next. No. Okay, yeah. Okay, this is a short detective story on Earth's rotation variation and the Earth's core wave mechanics. And but it cost us a long time. Indeed, our motivation is trying to understand from studying Earth's rotation, the fast dynamics of the core mental system. Okay, so as a detective story, so I will show you the criminal and the suspects and the criminal weapons and so on. Okay, first let's see what happened to us on the length of day, especially on the sub-decade scale. And first, this. Okay, and this is the LOD data from the IAS season 4. And if we are removing the background trend, then we get the residual, we call it the residual series. And here is the schematic spectrum of the length of day. And we know, and from the diennial to the seasonal, annual, seasonal, and it is well known for us that about the physical mechanics, including the tides, the atmosphere, ocean, hydrology, and so on. But for the long period, like decade, we call the decade fluctuations, it is usually recognized as the attributed to the core. But what happens in the core, we don't know. Yeah. So, and although we have a long list of the publications on the decade fluctuation of the length of day, but the mechanism for such kind of study are still unclear. Okay, let's see again on the residual LOD data here. And we use normal Morley wavelet transformation, MWT, plus our proposed BPME scheme, which is mostly used for to reduce the effect of the trial phenomena. And they found there are two primary periodic oscillations. One is the 6-year period, and another one is the 8.6-year oscillations. And one more interesting to us is that for the mean amplitude is about 1.124 and 0.08 millisecond respectively. And more interesting is that the amplitude one is stably damping and another one is amplified. And and this combination of gain. Okay, next about the weapon. Okay, and on the other hand, if we use the latest core surface flow data, which is inferred from a modern continuous satellite magnetic observation flow in this century, which was kindly provided by Gillett and his colleagues, and then we can calculate the torque of the electromagnetic torque exactly on the mantle boundary. And then after the flow data, provided by Gillett, and we adopt some key value for the key parameters like the electrical conductivity at the command boundary and the radio component of the geomagnetic field. Like this, then we can calculate the torque like this. Okay, if we compare. Okay, if we compare both of the what we do, we reduce the LOD data for the 6-year and the 8.6-year. This is the combination of the two periods, and then we can find that is the with the blue line is on the torque which we just calculated, and you can see that both of them are the identical periods. Yeah. So these results reveal the existence of the same periodic components, liquid core movement and LOD. And this provides us with new clue that the sub-decade LOD variation may originate from liquid core flow. Okay, so let's see again. Then we see these two periods one by one, and there are 3 potential mechanisms for them. One, okay, we just listed here, and we will see it one by one. Okay, for the first one, as on the torsional alpha variable, I will skip the technical detail of this model just to show you that it looks like the geostrophic model, which was used very often in the geodynamo society. And this data also provided by Gillett more than 10 years ago, and should also with the 6-year periodic and the torsional wave. And then we can use their flow data and calculate the torque as mentioned above, and then to compare with the LOD. Then we will see that this is for the 6-year. Okay, and for the 8.6-year, and we can see for the 6-year, both of them are corresponding very well, but not for 8.6-year. So it is shows that, okay, the 6 year, instead of 8.6 year oscillation could be explained by the torsional wave mechanism. Okay, this is for the 6 year. Now, how about the 8.6 year? Okay, and I will show you that what we get recently. It is 4 years ago. When we process the LOD data, and we just mentioned that we found the 8.6 year period. And one more interest is that the amplitude is increasing stably. And one more interest is that during each peak and valley, there happened geometric jerks, all of them. And then we try to see what happened between the LOD and the geometric field or geometric jerk. Okay, so we tend to this suspect. It's called equatorial magnetic Archimedes Coriolis wave. We call it EMAC model. And also just this model defined by this set of equations, and simply say that it's a stratified model of the flow, just which was confined at the top of the fluid near the common boundary. Okay, and then we can solve this equation and getting the induced magnetic field, and then we can calculate the Lorentz force and then the torque, and again. So we will see that from this derivation, we can calculate the geometric acceleration map and compare with the map which is from the geometric field observation, which was provided by the Duhong. And then you can see the compare and consistent with each other very well. So okay, but that's all, but not for the 8.6 year, because if we use this model, we can calculate the torque or the contribution to LOD is at least 1 order of the magnitude smaller than the observed or needed for the 8.6 year. So we just skip this one. Okay, then we move to the next one for suspension. And this we call the quasi-geostrophic magneto-Coriolis force wave, or QGMC model. But this model is mostly similar to the EMAC model, but the difference is that the flow is not necessarily confined at the top of the fluid core, but it's all through the fluid core. Then we can, so you can see the formula are similar. And then we can follow the same procedure and calculate the torque on the LOD on the mantle. Then we can let's just see the result. Okay, and the result is that this is for the 8.6 year, and you can see. Oh, of course. Sorry. I just forget to mention that there are some two key parameters to determine the torque. One is the let me see. Oh, sorry. Okay, just give. Okay, for the torque, we need the flow data, and this one is flow data, and it depends on some key parameters, which is related to the geometric field at the. Okay, just skip that. Okay, here is the beta and the Q. This is the quality factor, and then we just show some simulation of by different parameter of them, and to see what will happen to the 8.6 year oscillations. We just skip the detail, and okay, this is our final choice is for the cosine number. Which one is similar to the Gillot results? And this is the red one is the predicted 8.6 year LOD results based on the some above mentioned calculation, and the dotted line are the observed one. So you can see if we choose this model and the parameters, we can get very good result compared with the observed 8.6 year valuation. Okay. If from other side, if we agree that the 8.6-year variation can be attributed to the QG model, then we can infer that the velocity field of the core field at the inner core boundary, and this is a map and the RMS of the velocity field. Okay, okay. Sorry, just for skip. So very short conclusion, and so why is that? Okay, just why is that? The 6-year LOD oscillation can be explained by the torsional wave mechanism. Okay, and the next one is that this QGMC model can quantitatively explain the 8.6-year signals, including the amplitude and the phase. Yeah, okay. If we agree with that it will provide us a new approach to infer the motion characteristics of the liquid cores from LOD data. That's our motivation. Okay, thank you. And the last slide, just for a very short advertisement, that for the it's a journal of research in astronomy and astrophysics, which is hosted by Chinese Astronomy Society, and it's a monthly journal and in total free of charge. So welcome to submit your research work. Okay, thank you. Thank you.
Thank you. Is there any comment, question? Maybe you can.
Do you think that there might be the same reason for 6 years oscillation in polar motion excitation in LOD? How do you think? Because we also find these 6 years oscillations.
Yeah, but in polar motion, yeah. Very good question. We also tried to see in polar motion, but frankly say we didn't find. We didn't find. Yeah. But in principle, polar motion and LOD are the same. Just in the different direction. Yeah. Okay. See. Okay.
Thank you very much.
Okay. Thank you.
So thanks again. And now the next speaker is Alberto Escapa. So I will check for the time.
Yes. Take care.
It works.
Okay. Good morning again. I'm going to present some research about the dynamical ellipticity of the Earth that we have prepared with my colleagues Tomás Baenas and Jose Ferrandiz. First, I will recall some basic facts. As you know, we have the expressions of the principal moments of inertia of the Earth or any other extended body with these integrals. It is important to take into account that, in general, the bodies are not rigid. So even in a system linked to the body, these quantities are time dependent. A usual combination that appear involving these quantities is this ratio that it is named the Earth, in this case, dynamical ellipticity, also dynamical flattening, also precession constant. There are several denominations. And it is very important when determining the rotational dynamics of the Earth. For example, if you remember, the expression of the gravity gradient appears like this torque. And as you can see, in addition to some combination on the coordinates of the perturbing bodies, the moon and the sun in this case, we have that it is directly proportional to the dynamical ellipticity. In this way, when you are constructing a model for precession or nutation theory of the Earth, this quantity, the dynamical ellipticity, appears directly. So for different models of the precession and nutation of the Earth, both rigid and non-rigid, we have different values of the dynamical ellipticity accordingly the way in which the model was developed and the way in which the dynamical ellipticity was obtained. For example, we have here in the left column some values both for rigid and for non-rigid models, and also the way in which the numerical value of the dynamical ellipticity is got is different. One models just use the precession data, others make a data fit into both precession and nutation observation, so it depends. And the current one in use by International Astronomical Union comes from the precession theory by Nicole Capitan that was adopted as an official model in 2006. And this is the value that appears as a fundamental constant in the IERS conventions 2010 with some uncertainty, in this case 0.3 parts per million. From other point of view, the value of the dynamical ellipticity, it is also important to determine some mechanical property of the Earth, in particular the value of the moments of inertia themselves. In this way, as Bursa pointed out, the dynamical ellipticity is a central parameter because we need it to determine the value of the principal moments of inertia as I have mentioned. And the basic relationship is this equation. So in principle, you can get by satellite dynamics the value of J2, and with J2 and the value from the astronomical side of the dynamical ellipticity, you can compute the value of the, in this case, the moment of inertia C. The question here is that to employ in a consistent way this kind of relationship, it is necessary that the dynamical ellipticity follows the same conventions as the other parameters in these equations. In particular, it must follow the same convention as when providing the value of J2. In this regard, there is some more or less tricky issue that appears in this situation, and it is related with the treatment of the permanent tide. Accordingly, the way in which you are including or not the permanent tide, there are different systems or different conventions, and we have tide-free values, zero tide values, and mean tide values. Sometimes zero tide and mean tide are equivalent. In the case of J2, the standards usually provide its value with the tide-free convention or with the zero tide convention. So this question is explained in detail in the IARIS conventions. So the question is that we should follow exactly the same convention with the dynamical ellipticity. In particular, the recommendation of the International Association of Geodesy is to use always the zero tide convention. So typically we should use the zero tide value for J2 and the same for the dynamical ellipticity. The problem that we have is that up to now in almost non-astronomical studies are indication about what convention is followed to express the value of the dynamical ellipticity. And this question is relevant because it can make some difference about 26 parts per million in the value of the dynamical ellipticity, that it is above the current threshold. So this is more or less the context that it was the most important for me. So our work is to try to make some revision of the value of the dynamical ellipticity first, making clear what is the tidal system in use, mainly free or zero, and then making some update on the numerical values to get the final update. I will skip, of course, many details, so don't worry. Well, to obtain the value of the dynamical ellipticity when constructing a theory of the precession and nutation, there are several possibilities, but to make some brief explanation, one way is to obtain the value of the dynamical ellipticity from the precession, in particular, just from first order precession due to the moon and sun contribution. Then you establish one equation where you consider the first order precession, and this first order precession is combined with other contributions that you must evaluate theoretically, and the total amount gives you the general precession, that is a value that can be observed or estimated. That is more or less the way. So to get the value of the dynamical ellipticity, you have to just give this observed value and have models for this, in principle, a smaller part than the first order contribution. So typically, the question of the tidal system has to do with the fact that the value of the general precession takes into account or not the permanent tide. If you take directly the value of the general precession, the value of the dynamical ellipticity is a zero tide value. If you subtract the contribution of the permanent tide, the value of the dynamical ellipticity that appears is a free tide value. So it is more or less quite easy. Then with that, we more or less follow the same procedure as Capitan, and we consider several corrections to the several contributions to be added to the first order precession, but we extended the non-rigid contributions. We keep the same, the 4 first one, but we updated and added new non-rigid contributions in the second one. I will skip the details. And with all of that, we got the new contributions here in red color, and with our method that it is pure analytical, so you can change this. For example, these quantities depends on the values of the log numbers that are frequency dependent. We employ for the solid Earth the values of the IERS conventions, and for the effects of the oceans, the log number values given by Williams and Box in a publications of some years ago. And with analytical treatment, we have some formulas. We can determine the contributions of the non-elasticity of the Earth with the non-rigidity, and also of the contribution of the permanent tide. So we get an update value given by this quantity, where we can follow precisely what is the tide system used to derive such value. In our case, if we want to use the zero tide, that is our recommendation, we have this value. If we would find the tide free, we would have this different value. So we have more or less recomputed the value of the dynamical ellipticity, focusing on the tidal system that must be used, and our recommendation is independent on the value in every astronomical theory of precession and nutation. When providing the dynamical ellipticity, we should accompany this information with the tidal system, zero or free. And we suggest that in the next update of the dynamical ellipticity value, we could follow the last one with the last rheological models of the Earth. Thank you.
Thank you. Quick question.
Thank you very much. My question is, since the dynamical flattening is the global factor of the Earth rotation theory, including precession and nutation, so is it necessary to consider largest term of nutation, for example, 18.6 term in your study? Is it larger than the theoretical contribution of the precession? Because some of the contributions are very small. They are not larger than the main nutation terms. Thank you very much.
Yes, with this uncertainty about the tidal system, the parts per million would affect the value of the amplitude of the 18 GR term. So it is important to distinguish between the convention, if free or zero.
Checking for the online question, there are none. Maybe I will have one before we continue about the relation between H and J2 of the Earth. J2 is also not a constant over time. We have the rebound, or how does this affect and the value of H and maybe some other?
Well, that is a different, related, but a different topic. There is also some relation between the time variation, secular time variation of J2 and of the dynamical ellipticity. And in fact, in the current precession theory, it is assumed some secular trend in J2 to fit the precession. And of course, you have to take into account into the model of the dynamical ellipticity. So there will also be a linear term in time in the dynamical ellipticity, and it produces some small effects in the notations. So the whole pictures should be also a constant part and a linear part in time. The question is that the linear part is so small that for this topic, it is not relevant, the convention in the linear part, because it is very, very small.
Okay, so I leave the chair and give it back to you again, Alberto, for the last talk of this session.
Last talk is online in this case. You're here. So, well, then
on site again.
Then we have been lucky all the session. Then in this case by Tian, the development of lunar ephemeris with an Earth-type model compatible to the IRS conventions. Can pass here, pointer, and you have a timer there. I will give some indication.
Thank you. Okay, thank you very much. I'm glad to be here to present my work on the development of the lunar ephemeris with the Earth-type model compared to the IRS conventions. I'm Wei Tian from Shanghai Observatory. So my talk consists of 4 parts. So the first part, I would introduce the motivation of this work. So in the development of the planetary and the lunar ephemeris, figure effects and tidal effects in the Earth-Moon system should be considered precisely. And because of the coupling between the orbital and the rotational motion, the equation of 2 motions for the Moon should be solved simultaneously. And under this condition, so the impact of tidal effects in the dynamic model of the Earth-Moon system become very complicated. So with the advent of the lunar laser ranging technology, so the precise measurement of the Earth-Moon distance could be, is possible. So since 1969, the accuracy of the IRR was about several decimeters, and gradually, and gradually later on, it decreased to up to the level of several centimeters, and even better. And to the left, we can see the post-fit residues for 3 stations. One Weather in Germany, Aperture Point in USA, and the Grass Station in France. So, yeah. On the other hand, because of the more laser ranging stations have capability to laser ranging to the moon. So, and the observation of the infrared could be made in daytime. So the data coverage of the LLR getting improved significantly. So both the dynamic model and the observation model should be updated further. Okay. So the dynamic model used in the industrial version of our infirmaries is given in the right table. So we can see the orbital motion and the rotation model for the 2-layered moon are solved simultaneously. So in this work, that the updates to the dynamic models were made in the following aspects. The most important one is the Earth-type model. Sorry, consistent with the IAU conventions is adopted. So in the IAU's recommended job potential models, there are 2 parts. For the static part, EM 2008 is recommended, and the traction level in the table are suggest for a different orbit. But for the moon, the traction level usually we cite to 6 degrees. So for the temporal parts, so the effect of the solid Earth tide and ocean tides, etc., are considered. Associated models are recommended in the IAU conventions. However, the Earth tide model used by different infirmaries group are not fully consistent with IAU convention. So just a brief overview of the Earth tide model used in the planetary and lunar infirmaries. So there are 3 types: 1 time delay model, 2, 3 time delay model, and 5 delay models are designed by the GPR team for different version of their infirmaries. So for the 5 time delay models, that means the 5 time delay parameters are introduced in order to handle the frequency dependent effect of the degree 2. So recently I revised the Earth tide parameter of FTD model and further updated the tide potential tide parameters. So this graph depicts the comparison of the models in the infirmaries. So we can see the y-axis is the phase lag should be positive, and the x-axis is time frequency. So as the low frequency band, there's no different between the adopted models, or close to the IAU convention. So at the dynamic band, these three models are closed, but I mean DE 440 is closer, I mean, to the IAU convention model. At the semi-dynamic band, all the models passed M2 waves with the different slope. But however, negative phase lags for the S2 and K2 appear for the case of the DE 440. So in order to check the sensitivity of our solution to the Earth tide models, there are 3 final solutions obtained with the WT 2022, WB and DE 440 models respectively. However, 2 time delay parameters are fitted rather than fixed to the model value. So it is notable that in the tide model of FTD type, only progress terms can be incorporated into the model, and the retrograde term and crossover terms need to be considered separately. So let's check the static of the post-fit residues. So they are cataloged by stations. So, and time span and total observation and stability observations by the 3 sigma principle and weighted RMs. So we didn't find we didn't find significant difference in the rejection rate and the weighted RMs between the solutions. So that means it's difficult to say which model is better than others from the post-fit residues. So in comparison with the solution two of the Pavlov, in their solutions, the AR's convention model has been implemented on the APM platform, but in different approach. That's why the 2 time delay parameters do not appear in their solution. And so surprisingly, the results obtained in this work in good agreement with their solutions, especially for the lunar tidal delay, time delay, TAR2. So from with the estimated lunar tidal delay, so we got a larger lunar quality factor, than the previous ones. So more result on the lunar parameters. So for the love number H2, yes, it is very sensitive to the Earth-type model. So yeah, a consistent estimation of the lunar love number H2 with the one derived from the lunar environment is obtained in the case of the solution A. And for the another parameters A1, it is not as sensitive as the love number H2. So we also obtained estimation of the quality factor as 1 month from this parameter. So it's paradox. There is the paradox on the tidal dissipation in the moon. So as the terrestrial bodies, the quality factor Q for the moon is expected to have a weak depends on tidal period, but it is expected to be decreased with the period rather than increase. But I mean, based on our estimation of the monthly monthly and annual quality factor, we obtained a positive value for the P. That means the paradox can be resolved if we adopt the compatible tide model with the IAU convention. So conclusions. So first, it's difficult to judge which model is better from the post-fit residues. Second, in comparison with the results of Pavlov, the compatible results are abundant. And third, and the possible explanation of the paradox is provided. And finally, so we suggest the Earth-type model compared to the IAU convention should be used. Thank you. Thank you very much.
Thank you. Any question or comment?
How many lunar laser ranging stations are there total? You mentioned 3. Is this all what is operational worldwide?
Yes, I only mentioned 3. I mean, these 3 stations provide very high quality lunar laser IR data, but I think now there are 8 of 7 or 8 stations worldwide. Yeah.
I'm checking on online questions online. No.
Thank you again.
Again.
Okay. So thank you to all the speakers. This is the end of the session. We have to return to this room at 1:30 p.m. It will be the session 4 about lunar standards. Then see you later.
For the speakers?
Yes.
Or do you want me to keep the time? Okay, okay, thank you. And oh, okay. How is she?
Yeah, she's busy.
Mm. Got it.
The first is.
I know.
So we want you maybe to take 5 minutes before the end.
Okay, gotcha. I just put down the different times,
Yeah, okay.
but these are all world. These are all my.
Maybe you can take a few seconds. Okay, shall we start? So hello, everyone, and welcome back to this afternoon session of Division A, which will be this first session about lunar standards, chaired by Susan Stewart and from Commission A3 and on standards, and Brent Arginal, who will join us a bit later after his talk in Division F, who is chair of a working group of cartographic coordinates and rotation elements. And the first talk is given by Susan Stewart. So it's a 30-minute talk invited to present her thoughts about the lunar standards and the resolution that are also proposed at this General Assembly. So Susan, please.
All right, thank you, Daniel. Welcome, everybody. Welcome to those online as well. Glad to see you back after lunch. My talk serves basically two purposes. One is to tell you about the two resolutions that Commission A3 put up for vote, which you'll be voting on Wednesday, to explain them, put them in context, and then also talk about where we go from here, what other standards are going to be needed. And we're going to start the discussion on that. I may also add that we'll have talks this session, and at the very end of this session, we'll have time for about a 10-minute guided discussion where we can all contribute. So if you don't feel like you don't get your questions in, we'll have a discussion time at the end as well. Okay. Let's see if I can do this. Green? There. Okay. So the way this all started was talking about what we need for safe navigation on the moon. With all of the, or in or around the moon or to the moon, with all of the upcoming multi-nation missions that are coming up, what standards do we need for safe navigation? Well, fundamental navigation standards can fall into three broad categories. Reference systems and frames, which we're going to talk a lot about in this talk. Position and orientation of the bodies. And by that, we mainly mean position and orientation of the moon, and also time. So standards provide interoperability for safety and integrity of operations. All right, so I'm going to bring this up first, and this is the different international groups that work already on reference systems, position and orientation, and time. So we're not reinventing the wheel here. We do have organizations that for the Earth set standards, and these are internationally recognized bodies that have set a paradigm and also have a good record of working with each other and collaborating. So this framework has been relatively set up, and it's our hope that this will continue for lunar standards as well. So you can see there's a lot of overlap between reference systems and frames and position and orientation. You've got the IAU, the IERS, and then the geophysical associations, and then you have the time organizations on the right there. And we're just calling all these out. I know this isn't an inclusive list, so if there are others we need to add, please tell me, and we'll make sure we all get on the same page. Okay, we're going to start with reference systems, and how the context of what we're doing now is in. So the barycentric celestial reference system was adopted by the IAU, this body, in the year 2000. The origin is at the barycenter of the solar system, and it was formed because it is a lot easier to use a system with a center at the barycenter to do things like planetary ephemerides and catalogs and deep space mission trajectories, things that have the center of the solar system at its origin. One thing to note is that the BCRS does not have its own. There's no BCRF. There's no frame. The frame for the BCRS is the ICRF, the frame that's established, the inertial frame, which I'm going to show you here. The ICRS and the ICRF were adopted by the IAU in 1998 and 2006. So the background for which the space fixed axes reference system is tied, and it also has the origin at the barycenter, but the axes show no global rotation with respect to the distant extragalactic objects. I'm going to go back here real quick. And I forgot to tell, another point I want to make is in the orange box at the bottom. There's a lot of confusion on what the difference between a reference system is and a reference frame. So this is the definition that we've been working with. Reference system contains all the models, the whole system. The frame is actually a part of the system. What the frame does is attaches to real positions. So it attaches this coordinate system, these origin and everything else, to real positions. So we often say that a reference frame realizes a coordinate system. What that means is ties it to real positions. And it's part of this overall reference system, which contains many models to set up this navigation system. Okay. So now we can jump over to this. Okay, so this is the first step in our story here, or maybe the second. So in the year 2000, the IAU adopted what we call the GCRS, the Geocentric Celestial Reference System. It was adopted and proposed and adopted because we needed something that had the origin at the center of the Earth. Things like Earth-based astrometry, orbit calculations, Earth orientations, things that were done standing on the Earth, looking up, made more sense, especially if something was orbiting the Earth, if the origin of that reference system was at the center of the Earth. So the GCRS was established in the IAU, and there's a whole set of math equations, if you look in the IAU resolutions, that show how you can translate from the BCRS to the GCRS. It's relativistic transformation. It takes care of both time and place by using this transformation. It has a time, I should say. Its time, though, is what we call a coordinate time. Okay, that's another thing I want to teach you today. A coordinate time is not a time kept by a clock. It's the time at the center of the body. So you can't put a clock at the center of the Earth, right? To keep it. So T is just a theoretical time to put something in your equation, because you have to have time in your equation when you're doing these dynamical calculations. So it's a mathematical formulation of time at the center of the body. And this time is called geocentric coordinate time, TCG. So that's the time in the GCRS. Now, what we propose in resolution 2 is to create an LCRS by the same methods that we created the GCRS. So it's a relativistic transformation, taking into account general relativity, and it transfers from the BCRS to the center of the moon center of mass, sorry. And it's done by the same principles. So literally, what we have proposed is to take the original resolution for the GCRS and replace the constants for the moon. And it works. And in fact, you could do it for any body, not just the moon. There's nothing special about the moon. It's just what we're talking about right now, because it's what's needed. Why is it needed? Well, if you're making observations from the surface of the moon, you don't want to use a coordinate system that's the surface of the Earth. I mean, it just doesn't, mathematically, it's not the most convenient thing to do. So our resolution, our second resolution for vote Wednesday, is that we propose we do the same thing we did for the GCRS now for the moon, create this LCRS, and we also create a lunar coordinate time, TCL. And remember, this is the time at the center of the moon. So there's no clock at the center of the moon. So there's a lot of talk about time and how we need time is different. This is a theoretical time. It's equivalent to, not equivalent to, but it's the same concept as the time at the center of the Earth that we've already proposed and used. Again, you would use this for moon-based astrometry and low lunar orbit calculations, things that are being done with the moon, operations with the moon at the center. Okay, all right, and this drives home the point I was trying to make between coordinate time and coordinated time. There's just a D that's different between the two, but there's a big difference. So time kept by a clock, you hear UTC, Universal Coordinated Time. That's a proper time. It's kept by a clock on the surface. But coordinate time, again, is this mathematical construct. So TCRS, so TCG is the coordinate time for the GCRS, TCB for BCRS, and now we have TCL for LCRS. These are all four-dimensional relativistic transformations. Okay, so again, I'm going to drive home the point that we have various international standards organizations coordinating with each other. That's why I drew these concentric circles here. Both the GCRS and the BCRS were established by the IAU. And then you have the IAG, that is established the ITRF, and there's other organizations that have done a terrestrial frame linked together. Those two are linked together by the IRS establishing the EOPs, the Earth Orientation Parameters. So the key to connecting those frames from a surface frame to a celestial frame is knowing the position and the orientation of your body. So this is how it's the paradigm that's done for the Earth. And what we're proposing is that we have an LCRS established by the IAU. It's tied to the BCRS. And then we have LOPs, lunar orientation parameters, that we need to establish some sort of a place. We can discuss how best to do that. And then we have a lunar geodetic system and frame, of which we really don't have a name for yet. I've heard it called several things, but that would be the equivalent of the ITRF, so the surface frame of the moon. We still need to coordinate with whoever's doing that to make sure that it is in collaboration with the celestial. And note there that there's also the proper time UTC on Earth, and then on the moon, it's being evaluated how we would have a proper time that would be used by the the surface frame. Okay, mentioning the surface frame before, this would be the body fixed frame for the surface. So this is when you're navigating on the surface, you would use something like this. So we would aim for some sort of standard. There's several standards that exist for Earth. We need to discuss how that's going to happen for the moon. It needs to coordinate many things, a coordinate system, orientation model, gravity model, a shape model, the geoid or the lunar geoid, the reference frame, etc. It also needs a time system to be able to use it. And that's where I was speaking of the proper time. Okay, so what about time? All right, this embodies the third resolution that we have proposed for Commission A3, and that is that a standard coordinated time, not coordinate time, but a standard coordinated time for lunar operations and applications is needed. And our resolution 3 calls for international coordination to study these considerations. It still needs evaluation. And we call for the international bodies to work together on establishing that time, that proper time. We are calling it LTC, lunar coordinated time, just on the same premise as UTC is named LTC. So that's the crux of our resolution. It's to establish this, to work together to establish this standard time. Now, why is this still being evaluated? Why is this so difficult? Main thing is the different potential of the Earth and the moon. There is a linear offset based on the different potentials. So if you have a clock on the surface of the moon and you have a clock on the surface of the Earth, they will differ by 56 microseconds a day. So that's one linear term that you need to deal with. And that is pretty well established and agreed upon. The problem is that there's still offsets, and there are periodic terms that are not yet well understood. There's a monthly term. You can see the monthly in the monthly orbit. There's that term, and there's also a annual term going on as well. So the graph on the right is the difference between the two coordinate times, TCL and TCG. So at the center of the moon, this is how things are differing. And so there's also maybe even larger variations over an annual or multi-annual time frame that need to be understood if we're going to establish a time standard for the moon at some point. So one other thing I want to throw in there, just because I'm representing the Standards Commission here, is that we also recognize that we need some new terms, and we need to all agree on what terms are going to be used for these things. The IAU used to have, or did have, a working group in 2006 for standard terms in glossary, and policymakers and news media, et cetera, when they go to a source, we should be proud that they go to the IAU. We're considered the standard. So we haven't had an update since 2006. Latest revision was 2007. And I've drawn up there, just for example, one of the terms that's always confused, and that, what is cislunar? Everyone uses this word cislunar. So one of the things that we've been going off of is this diagram here, which basically means whatever you're talking about, it's in the spherical volume of space defined by basically the Hill sphere of the Earth Moon. So everything that is gravitationally affected within that sphere dominant by the Earth and Moon would be in that. So it's approximately a sphere with a radius of 465,000 kilometers, give or take. But that's for example, that's what we're using. That's not a standard yet, but we were just suggesting that. So the things that I've been talking about in here, I've already made up a couple terms there that I've been speaking about: LTC, LCRS, TCL, LOPs, and also the surface frame, which has been called several different things, from the LRS to other things. So we need to standardize these terms. And we'll be discussing that, adding a working group in the Commission A3 to reestablish this group. So you're welcome to join that, should you like doing this kind of things. So where do we go from here? Well, several international bodies have started lunar working groups, and there has been a good bit of collaboration so far, but we're here. If there are others that we need to hear about, we would be open ears for that. The IAG, the International Association of Geodesy, has formed a working group on lunar reference frames, and they are concentrating on the surface frame, so that the frame on the surface, and they have formed a working group, and I think they're going to be presenting at the AGU in the fall. But there's a lot of coordination between that group and the IAU standards group. So we've been having a lot of communication with them. The IAU obviously has Commission A3, which is the commission that has just proposed the resolutions. I will also put a plug in for the IAU symposium that was just awarded by the IAU on advancing reference systems, ephemerides, and standards from Earth, Moon, and solar system bodies, August of 2025 in La Plata, Argentina. It's IAU Symposium 200 or 20 or Alberto, what is it? Okay, thank you. Forgot the number. And the thing I like about that symposium as well is we're not doing the moon in a silo. It's considering all bodies in the solar system. So we're going to coordinate standards amongst the bodies, so they're not being picked off one at a time. There is also an IAU working group on time and frequency. They have formed a lunar time subgroup, and there's been some conversation. The BIPM, who establishes UTC, they have formed a group for discussing lunar time. Waiting to hear what comes out of that. And then there is the International Committee of GNSS, Interagencies Operation Advisory Group, Lunar PNT meeting in 2025 that's coming up. And they're forming some sort of subgroup there as well, or working group is the ones I know about. Okay, so to summarize, the current recommendations that are up for vote on Wednesday, I think it's Resolution 2, basically defines the lunar coordinate system, the LCRS. So the reference system for having the moon at the center, and the coordinate time, TCL, that goes along hand in hand with that LCRS. The second is simply that a coordinated time needs to be established for the moon. And we call the different organizations to work together to do that. Future considerations are needed, and this is some of the some of the things off, that we need to talk about to continue and to address. We need to have a body establish the standard surface reference frame. And what do we call it? LRS, LFRS, coordinate system reference frame, et cetera. All of that needs to be tackled. Still, we need to define the coordinated time, as I just said, from Resolution 3, and update the standard terminology, and then talk about extending what we're doing to the moon, have it extensible to other solar system bodies, so we can tackle this in a way that considers future exploration and whatnot. So that's all I have. Again, we're going to have a discussion at the end of this session for about 10 minutes to talk about some of these things, about what standards we need. I know there's many more. This just scratches the surface. So in any case, thank you for your attention. I'm here for questions.
So there are two recommendations to be voted on. How do you see them sort politically? Is one excluding the other? I mean, does it matter which one is adopted and which not? Or can one interpret the second one as being open to further alternative definitions?
They are separate because they deal with a separate entity. So the LCRS and the coordinate time can exist without the proper time resolution. Like I said, the proper time needs a lot more evaluation. We're not ready yet to make a recommendation on that. And we may not be the body to do that. I mean, we have some working groups, but there's a lot of different people that work together. And that's the most important part of that third resolution, is a call for people to get ready and go forth and, evaluate the time. Because the timeline of the missions coming up, they're going to be here before we know it, and so we need to have this discussion. And so that's what the third resolution is about, is just a call to the organizations, the relevant organizations, to do that. Did I answer your question? Okay.
Other questions? And if there are questions online, let me also check these. Please put them in the chat, or we can open the microphone. I think. There is a question. I wonder if I can comment online. Yes, please. I don't know.
I don't know if you can hear me.
Can the online speaker speak directly, or I just... Yes, you try it, Sergey.
I'm trying. Can you hear me?
Yes.
Okay. So I only wanted to say that Resolution 2 describes the basic formulation, actually, and there is no alternative for that. And Resolution 3 is only discussing a possible scaling of the coordinates and timescales which are introduced by Resolution 2. The scaling is free in principle and independent, and this is a separate discussion on which I will put something on my slides, but it is certainly a longer discussion. We have no consensus on this scaling right now. It's just I wanted to comment this.
Okay. Are there other questions or clarification? Yeah.
Okay. So as you stressed, there's a difference between a time coordinate and a proper time. And the proper time is in principle measurable by a clock. So the question is, if I understand correctly, the coordinate time at the center of the moon excludes the moon's gravity, but it does include the effects of the sun's gravity and the results of the moon's orbit. And so I guess the monthly and the yearly variations are due to the moon's orbit, right? Yeah. So sorry with that. Okay, if I understand the thing correctly. So the question is, when kind of future generations of clockmakers make their clocks, which are good to 10 to the minus 18 or whatever, Will there come a time when the resolution 3 needs to be revised, or is it now and forever, as long as the laws of physics apply?
Is my mic on? Yeah. Yes, there will be. Basically, what resolution 3 calls for is for that to be done. We want to set that process in motion for someone to make a recommendation or to agree upon a standard, because we don't know it yet. We have ideas, but we still need lots of evaluation and lots of smart minds working on it. But yes, it will be, hopefully, it will be replaced with a standard.
Another question for this talk.
Thank you for this nice presentation. I'm just wondering if you consider height system part of the standards or just celestial reference system?
Can you repeat that?
Height system.
Height system?
Yeah, as a part for geodetic application.
For the surface frame?
Yeah, for the surface. Are you consider it part of the standards?
That will be part of the lunar reference system, the surface frame. Yes, it will be eventually, but there's not the current resolution. It's not part of the current resolution is just for the space, the celestial reference system up, but we're waiting. We're going to get there.
More questions? We still have time for clarification of this talk. And then again, there will be, we'll keep time to have a general discussion at the end of the session. No question here. I don't see online. Again, if there is a question online, please put it on the chat. If no questions, thanks, Susan, again, and I give you the chair of this session. And the next talk is by the co-chair of the session, if I'm correct. I am Brent Archinal, who gives the talk online about the cartographic lunar reference frame. Brent?
Okay, can you hear me okay?
Yes.
All right. All right, so go ahead and get started. Yeah, so this is a talk about the cartographic lunar reference frame, which is not coincidentally basically the lunar fixed reference frame that Susan was just talking about, and the current existence and definition of that frame. So we'll go ahead and present here on the main topics, as long as I get the slides to advance. So the main things I'm going to be covering are two overarching topics, and one is the updating of the existing mean Earth polar axis system lunar cartographic reference frame, and also the consideration of the use of a principal axis system-based frame for that purpose for mapping. And I'll just add a little note here that this presentation tracks work from the IAU working group on cartographic coordinates and rotational elements, but it's actually only authored by myself due to various logistical reasons. This has already sort of perhaps been known or covered, but there are two common lunar reference systems. And again, as maybe Susan covered, I didn't hear the beginning of her talk, you have both systems and frames, systems being theory and conventions to have an idealized model, and a frame that actually defines point coordinates. So there's the mean Earth polar axis and the principal axis systems for the moon. The mean Earth system is originally defined as the mean direction of the Earth defines 0 degrees longitude, and the mean direction of the moon's polar axis defines latitude. And this has been in use in some form since the 18th century, and certainly for all of the space age. The principal axis system has 3 moments of inertia defining it, and it's important for dynamical purposes and gravity field studies, spacecraft force modeling that uses those gravity fields, and so on. The difference between these systems varies, but is maximum of 875 meters. And this is due to the symmetry in the lunar gravity field. But this is obviously significant given the resolution of current lunar data and data sets. So right now, this IAU working group has the responsibility to make coordinate system recommendations for all solar system bodies other than the Earth. And these recommendations are for cartographic purposes, so they don't preclude the use of other dynamical systems and frames. But that's why I call this a cartographic lunar reference frame, because that's the real goal here. The underlying frame for the moon is given by a lunar laser ranging solution and orientation models. And for example, the current definition follows the JPL DE 421 solution and ephemeris by Bill Fultner and others from 2008. But this is accompanied, it's done in a PA system, but it's accompanied by a 3-angle rotation to obtain the frame and orientation in the ME system, with the rotation given here. And this has been recommended by the LRO mission and the NASA International Lunar Geodesy Cartography Working Group in 2008, and by most space agencies worldwide. The working group itself affirmed those recommendations in its 2011 and 2018 reports. Further updates of the frame need to be done with a no net global rotation of the solution so that the coordinates of features are maintained. In other words, use the ME421 frame to orient the upcoming or existing new DE440 frame and ephemeris. The internal frames in ME and PA for 440 are the same. The only difference is this global rotation that maintains service coordinates. And as I've highlighted here, that's the whole point. You need to maintain the coordinates of features when updating a cartographic frame, so there's no confusion resulting in a need to move data sets around, basically. So the question is, should there be at least some improvement made in the cartographic lunar reference frame? And this has been discussed over the last several years by various NASA and other working groups. These reports, as shown on the right, the NASA League group came into this last year, as did the NASA Planetary Science Advisory Committee. And the idea is at least to make some sort of update. And this could be done by using the new lunar ephemeris, already mentioned, the DE440 ephemeris by Ryan Park et al. From 2021. This incorporates new lunar laser ranging data, improved models, a new lunar laser ranging solution. But again, the critical feature is a no net rotation condition so that coordinate changes are minimized. The changes are not very large between the old and new. I'll show some differences in the ephemeris on the next slide. But the difference in the actual lunar coordinates is an RMS of about 9 centimeters. So this is not significant to be noticeable except at the highest levels of accuracy, but some people seek out these highest levels of accuracy, and it does actually improve LROC imaging positioning. In the future, other types of updates or alternate versions of this could be done using various multiple LLR solutions or even eventually solutions from other techniques. Just a quick plot summary of a couple of plots here showing the differences in the ephemeris. The upper plot shows the XYZ changes over the period of, say, the LRO mission, the early 21st century, and the changes essentially total to about 40 centimeters maximum. And these changes are presumably because of improvements, but of course there's no way to know. You're comparing one system to another, and these are the changes between them, which presumably are due to modeling and data improvements. The bottom plot shows the total change over the 20th century and first half of this century, showing again most differences are in the 40, 50 centimeter level for the period of lunar laser ranging, a little bit higher over the entire time period. So the other issue that overarching issue here is that recently several groups have proposed using a PA system for mapping and lunar navigation. But so far, there appears to be no actual proposal of what change would be made and why. In other words, which PA frame would be used, what are the requirements that need to be met, why can't a ME frame be used to meet any requirements, and what other issues might there be with the current definitions, with the current ME system and frame. So just covering this briefly here, that obviously the benefit of a change is not clear when there's not a good specification of the need for the change. Successive ME frames do provide for an accurate cartographic frame by minimizing changes in coordinates. And again, this is the critical goal for cartography. Such a change could even be applied to successive PA frames, but that's not done currently. And the working group itself has had this long-standing recommendation that once an observable feature is chosen to define longitude, that system should not change. And that still seems to be a very reasonable recommendation. And for the moon, a change in the position of the laser retroreflectors of 875 meters seems extreme given current data sets. So the major concerns with such a change are the need to move some or all lunar data from one system into the other. You need some sort of plan to do these types of changes. The costs would be substantial and require funding and the use of already overcommitted personnel. It would be a massive undertaking if you converted most or much of the data, since all lunar data is in this system, all imaging and LiDAR data, which means several petabytes of data worldwide, millions of images, billions of LiDAR measurements. Confusion between these systems would be an ongoing issue, as users would then start to need to carefully check which frame their data is in or which frame they're operating in. Some users or space agencies may not switch, resulting in an indefinite period of confusion. There could be even navigation concerns as different groups use different systems. The convention will differ from the Earth, where mapping in the International Terrestrial Reference Frame or even the WGS frames are all not in PA frames. So just some brief recommendations that to consider such a significant change, a proposal of what will be done and why needs to be published and needs to be considered and widely discussed. And international space agencies, the IAU and other groups, as Susan actually discussed, need to consider such a proposal and provide input. I'll add that the NASA Federated Board, which is sort of a management board for NASA, has created a working group to look into recommendations for a NASA-wide decision, and a result on that is expected soon. But no matter the outcome, certainly better international cooperation on standards for mapping and navigation would be useful. It's been suggested that possibly an international lunar year may occur soon, as proposed by the US and others, and this would be a good topic to cover as part of that effort. So I'll finish up here that the main point is to ask for feedback. And again, speaking for the working group as a whole, I think they have repeatedly stressed that the idea is to ask for feedback, whether on minor or major changes in the lunar reference frame. As to updating it in the minor sense, should the current new LLR solution be used from JPL, the 440 solution in ephemeris? Is this appropriate? Could some other frames of some other solutions be used and rotated instead or in combination? And what changes are needed to be made in the future? And finally, regarding any change in the reference system, what are the current issues in using the mean Earth system for cartography for a lunar reference frame? And what advantages would there be in going to using a principal axis frame in comparison to the substantial effort and confusion that might result? So certainly feedback is welcome to me by email or here at this meeting, virtually, of course, but we're certainly open to comments. So thanks for your attention.
Any questions for Brent? Anything online? Let me check online. Okay.
I don't know if Vishnu.
Hi there.
Are there members from the LLR analysis community in the working group or cartographic coordinate rotation element? If not, it would be good to include some experts. So the question is, are there members from the LLR analysis community in your working group, Brent?
Yes, I would say right now there is not somebody working specifically in that field, but we have a few people who have asked to join and probably will become members maybe in a matter of days or weeks and be helping the working group. Certainly you and others are welcome to join the working group too if you're interested in participating, but we'd appreciate as much expertise as we can obtain.
That sounds like something we need to add to the discussion list for our to-dos and what is needed. Anything else? No. Well, thank you, Brent. Appreciated.
Okay.
Okay. So our next talk is from Vishnu Viswanathan, and it is on lunar orientation, which is coming up online.
Hi there. Can you hear me okay?
We can hear you. Can you start sharing your screen?
Yes.
And we can see you. Perfect.
Right. Okay. Well, thank you to the chairs and the organizing committee for the invitation to the session. Today, my talk is centered around our knowledge of the lunar orientation, and I'll try my best to cover two different timescales, but I think that's also relevant here. So this is my general characteristics slides, also known as setting expectations right. So when I mean geological timescales, they're kind of hundreds to millions of years to the level of few billion years. And they mainly rely on like indirect measurements, and which also means they likely involve very simplifying assumptions, and therefore involves a relatively higher uncertainty in the results obtained. All right. And on the contrary, modern times means more like daily to decadal timescales, and we have more access to direct measurements to support these findings, and thus relatively low uncertainty. Now, I want you to look at this impact basin on the moon. This is roughly like 1,000 kilometers across. It shows the shaded relief obtained from digital elevation models and superimposed by the color map that gives you an idea of its gravity field, which is essentially a measure of how the mass is distributed relative to that reference sphere. Now you can see how an impact of the scale has modified the moon's mass distribution, and also how the moon has preserved this bombardment history into its gravity field, which was recovered in very high resolution through the analysis of tracking data of the Grail spacecrafts. Now, let's say we were to try and understand how the moon's pole would have wandered due to such impacts. One way we could deduce this is by subtracting the signature of such an impact from the gravity field of the moon to get an approximation of the gravity prior to the impact, and essentially trying to find the low energy state of the moon's orientation or the principal axis of rotation. Here you can see the reds represent mass excesses, and the blues and the greens they represent mass deficits. Okay. Now, if you look at the moon's gravity and topography, we know that there are both large, of the order of hundreds of kilometers in diameter, as well as small, which is lesser than that, impactors which have left their signatures on the moon's surface, and it's relatively untouched by impacts. And so this gives us a very good insight into the history of the moon's orientation as a way of modeling. So this is how it would look like. We can make models of each craters and then erase them from the gravity field of the moon. And this helps us to understand the gravity prior to that impact, right? Now, if we do that over a period of time, now we know the moon is bombarded over its 4.5 billion year history. And as the bombardment reduced, the impact of population also reduced in its vicinity. So based on a crater production rate, known age estimates, and some randomization to allow variability, we can kind of get an idea of their distribution as a function of time. And if you back integrate this over geological timescales, ignoring all the transient effects, one can really map out the geographical location of the pole as the body reorients in space. This phenomenon is better known as true polar wander, and it mainly results from centrifugal forces acting on the non-uniform distribution on the surface or within the quasi-rigid body, pushing all the mass excesses towards the equator and the mass deficiencies towards the pole. So what you see here is the moon's polar wander, or the reorientation in space, mainly from impacts, which is sized to a level of few kilometers. Now, this tells us that the moon's pole was not in its present location, which is an interesting fact to consider as we head to the moon's present-day poles, right? Also, we are not the first ones to report on polar wander of the moon, but our work is definitely one of the comprehensive ones when it comes to consideration on the number of impactors modeled. Now, while this is an estimate, we are yet to find other independent estimates that concur with this path, and that's the pinch of salt. But what we do know is that the moon's pole has been relatively stable to within a few degrees or less than 2 degrees since the Oriental Basin Formation, which is the basin that I showed you at the beginning of this talk. Now, the total movement that you see here on the right, that's the South Pole, is about 10 degrees, and it's in a direction along the Earth-Moon tidal axis. Now, if you look at the figure on the right, for reference, all the candidate sites for Artemis 3 are within that dotted line, or the 5 degrees of the moon's pole. Now, if you want a more recent orientation model or more accurate one, the way we do it is using numerical integration and fits to high accuracy geodetic data, such as lunar laser ranging data. They involve the modeling of the precise talks between the way it is done now. It involves the talks between the different layers, which means there's also a consideration of the gravity field of the moon that enters into this equation. And sometimes even the knowledge of the interior density profiles obtained from seismic data analysis really helps establish constraints, right? And so monitoring the way the moon rotates, it also helps us to deduce its interior properties. And this was characteristics like its interior structure, core ablateness, which are some of the studies that I've been a part of. Now, the lunar laser ranging data, it's one of the fundamental lunar data sets that has really enabled a multidisciplinary science return over more than 5 decades now. It's still operational, and the data span is increasing, which is nice. And it starts at about 1969, which these are really time of flight measurements that provide two-way range between an Earth station and a reflector, a retroreflector placed at the moon's surface by either the Apollo astronauts or on the lunar core rovers. Now, the analysis of LLR analysis has really enabled a wide range of studies, which has contributed to lunar planetary science, earth sciences, fundamental physics, and celestial mechanics. All right, this is how the residuals would look like. So that's the annual weighted RMS of the LLR post-fit residuals as a function of time. Now, there are several engineers and researchers across observatories that have really improved this measurement technique over decades. So hats off to them. And these facilities have really obtained these high accuracy LLR data, and they've made them publicly available to the community through the ILRS, which is the International Laser Ranging Surface. Now, these efforts have really enabled us to understand the deep interior of the moon. For example, we can see the time series here, and the colors are different model complexities. So yellow is one of those rotational model where we don't consider any dissipation in the core mantle boundary of the moon. In cyan is when we consider the dissipation from a fluid core, but we assume a spherical core. And at the bottom, where we introduce some level of non-sphericity at its interface. And you can see the residuals get closer and closer to the observations in the modern day time. But as with any answer, there's always room for improvement in how we model this. Now, one of the use cases for lunar laser ranging data and their analysis is for the definition of lunar reference frames. And we have had talks related to this today morning. And the coordinate and the uncertainties of these reflectors are really critical to the realization of the lunar reference system. And as we know the position of these instruments quite well now. Now, the millimeter level data that you saw before, its analysis, what they result in is close to centimeter level, or even sometimes tens of centimeter level uncertainties on the retroreflector coordinates, right? And the analysis, as Brent mentioned, it's done in the principal axis frame, primarily because that's the method frame. That's a frame wherein we have the equations for motions available. And so this scaling, the inflation of this uncertainty when it comes to the reflector coordinates, as in comparison with the LLR data, is primarily because of the non-uniqueness of the model parameters used whenever there is a fit involved, right? And this is something to keep in mind, that fits introduce a level of uncertainty. Now, this slide wherein I'm showing on the left, all right. Yes. So on the left is, you can see 5 subplots. Each of them are for each retroreflector. So A11, A14, which is the Apollo reflectors, and the bottom 2 rows are for the lunar code reflectors. And we have obtained uncertainties associated with it for each of those 3 coordinates, the X, Y, and Z components, as you saw from the previous slide. And that's the component on the left. Now, remember that that's in the principal axis coordinate system, right? The minute you transform that into a different frame, you would carry over an additional set of errors. And this is primarily because the transformation between them comes from a constant rotation, right? And those constant parameters, which is often quoted in the literature, they are obtained from a fit. So, which are the values that you see on the top right for the different ephemeris, like the D421, D430, and D440. And so what happens is that if it's really a constant term, then the panel on the right would be 0, right? But unfortunately, it is not, because there are some uncertainties associated with that 3-axis rotation to go into the mean Earth frame. So this is where essentially where the root, where the principal axis frame kind of carries on additional uncertainties. And so the total uncertainties when it comes to the mean Earth frame, it would be the quadrature sum of the panels on the left and the panels on the right. This is unfortunately not very well understood and not very clearly explained in the literature. So I understand where the confusion can come from. And you can see how that really adds on to the level of about 1.7 meters in longitude. That's the error that you would get on those coordinates. And the error on the latitude is much less. And that's primarily because in the longitude, that's where most of the long-term effects come in on the longitude libration of the moon, right? And so these are really constant terms of the polynomials which are fitted and not really constants. And the literature where you can look up these numbers are the Rambo and Williams, which is essentially how they establish those defining terms, so to say. So I know that there's been a lot of talk on this, and this is essentially applicable mainly for coordinate positions or accuracy requirements of less than a meter, like Brent mentioned. And so while using those ME frame coordinates, particularly for applications which are less than a meters at the surface level, it's caution advised, because we should think about future applications, and much of the dominant errors in that comes from the component along the y-axis, which is essentially along the libration and longitude. Yeah, so you can quote me on that. And I'm happy to pass on the analysis to the working group. I believe I already have through all the sources, but happy to chat more on that. Okay. And so I do agree that we really need a roadmap for improving the lunar reference frames. And the reason why is that much of the decisions that we take today, unfortunately, they're relied on past data, on the data available, and also the past and current applications that we can think of. Rather, I feel, and this is my personal opinion, that it should be based on future data and future applications, which encompasses, which I presumably more improved data, right? A very nice example is how the ME frame came to about, primarily because there was a very large uncertainty in the lunar gravitational constant, the gravity field of the moon prior to the GRAIL mission. And so those were really the dominant contributors that were present in the lunar orbit and orientation obtained from FITS to the LLR data. And in the future, as the low degree and the order spherical harmonics of the gravity field they kept improving from newer solutions of GRAIL, we had coordinates with respect to the PA, which became much more stronger and stronger in terms of accuracy. So this is something to think about. And how do we go about improving? I think what is really helpful is much more higher accuracy geodetic assets on the moon. Prime examples is next generation of retroreflectors, which are I'm hearing an echo. So the next generation of retroreflectors, which are single conic cubes rather than array, they really help to have very high accuracy measurements, and that's the near term. Thank you for that, Bell. They are definitely helpful to establishing and improving the lunar reference frames for the near future. But we may also want to think about how do we establish and maintain a new and independent ties to the available inertial reference frame. And thank you, Susan and others, just to make it easier for me to communicate. I don't have to explain, reference frames versus reference system here. And so the instruments we're looking at would be like zenith cameras from the moon surface, just to ensure that there's a direct tie available to the inertial frame. And I fully agree with Susan that there is a lot of room for collaboration, particularly with the larger Earth geodesy. No need to mention Earth because geodesy means the Earth, but there's a lot to learn from that community on how reference frames can be maintained over long term and support high accuracy applications. So really our aim as a community, I believe, should be to enable that path towards a long-term frame accuracy and stability, and really address the needs of new applications in that growing cislunar economy that we're witnessing today. Yeah, all right. Thank you.
Okay, let's thank our speaker. Questions?
Thanks for your talk. I have a question. Could you jump to the last slide?
This is the last slide.
The last the previous slide. Yes. I was wondering why the dominant errors occur for the Y component, not X component, because as far as I know, so the X component is highly correlated with the mass parameter of the Earth. So my question is why component, not X component? Thank you.
Yes. Yeah, thank you. That's a good question, relevant question. Remember that here I am quoting the ME frame and not the frame in which the data is analyzed. So if you look at this particular chart, so you can see that much of the errors is along Y axis, and that's true relatively when you compare both the transformation error as well as the coordinate error, and that's primarily because the sensitivity of LLR data is along the X direction, right? So major improvements in how accurate the data is, the modeling, you would get improvements along the line of sight. Whereas in the orthogonal direction, which is along the orbit of the moon, you would take in errors coming from modeling the torques, because that's the direction where we have lack of sensitivity when it comes to LLR data. And this is also why it's recommended that we make radio observations potentially with radio beacons on the moon and try to really minimize that transverse error. I hope that answers your question.
Okay. Anybody else? Sure.
Thanks for the talk. This is Ryan Park from JPL. Unfortunately, I do see a number of wrong claims and flaws in your presentation, and you probably have to have another maybe side discussion. But first of all, the claim about the fact that the ME frame was defined based on the E421 is not a fair statement, because the E440 includes all the updated gravity field from the GRAIL data, and the ME frame was defined relative to the PA frame from the GRAIL-based lunar gravity field. So the numbers that you're quoting based on the Jim Williams personal communication is just not a good representation of the E440 uncertainty ME frame. So perhaps we should have a side discussion, but unfortunately, the one slide after this, we're going to quote on you at some point, but that is a wrong quotation in my opinion.
All right.
Definitely less than 1 meter level.
Well, I don't have any comments on that, but I'm happy to discuss.
And maybe we'll have more time later at the discussion. There was another clarification question from Brent Archinal. Which type of mean Earth system frame is being discussed?
Yeah, could I maybe clarify? Could I clarify that, Daniel and Vishnu? Yeah. So I'm following up here with a question similar to what Ryan mentioned, in that certainly if you rederive the mean Earth frame from first principles, you're certainly going to see some movement in the frame depending on the gravity field, and you're going to get a different frame than you would have gotten from DE 421 ME. But that's not the goal. As I was saying in my presentation, the goal is to improve the coordinate system without on average changing coordinates. We're not trying to recreate the original mean Earth system. We're trying to create a frame that doesn't move from the past frames. And the work that Ryan has done, the DE 440 frame, as I mentioned, has a change of only 9 centimeters RMS between the ME 421 frame and the 440 frame, while the principal axis frame has an RMS of 27 centimeters. So if you use successive principal axis frames, you're going to see bigger changes in coordinates than if you use this no net rotation principle. And this isn't an unusual principle. It's used for the Earth. So if you're saying that this no net rotation idea doesn't work, then you have to reevaluate all the coordinate systems being used for the Earth, the ITRF, and so on. It's just not clear why that system would be a problem. And lastly, just to elaborate on that, the rotation that Ryan has determined between the two frames is a fixed number, and it does involve a fit between the old and new systems. But once you've done the fit, it's an exact rotation, and there's no uncertainty in it.
Well,
I'll stop there.
Fit involved, I'm sorry, if there's a fit involved, there is some level of uncertainty.
Yes, and it's 9 centimeters right now. The level of uncertainty in that fit is 9 centimeters.
Yeah,
It,
what
you
I'm
know,
saying
that's much better than the 1 meter that you're claiming for
yeah,
an
what I'm
ME
saying
frame.
is, what I'm saying is it's debatable. Yeah.
Okay.
Well, we're debating it, yes.
How about we debate this longer in the discussion session so we can move on? Thank you, Vishnu, for that, for your presentation. Next, thanks. Next, we have Sergey Kilioner is going to speak to us on the question of lunar time, lunar proper time standard.
Yes, can you hear me?
Yes, we can hear you.
That is good. So, just a second. We will remove all this. Okay. So the topic of my presentation today is the time of the moon in the context of various relativistic timescales in the solar system. The point is, what we have now started to discuss concerning the moon should pave the way towards the future applications with other solar system bodies like Mars, which will come maybe 10 years later. We don't know exactly, or Mercury, and maybe Venus, but at least this Mars and Mercury. So let me remind you that in the so the IAU has a very beautiful framework, I would say, for relativistic modeling of high accuracy observations. This is the IAU 2000 framework, I remind you, and it was defined, so this framework was defined by several resolutions, starting from IAU 2000, and then improved or some added features were, some additional features were added in 2006. And this framework is based on a series of publications by a number of experts in general relativity since the beginning of the 1990s. So these are some references, and we have also explanatory supplement of that for that framework published 2003. Well, in between these two these two periods, so after year 2000. This is a post-Newtonian framework, but from the features of the, mathematical nature of general relativity, for the time, this is post-Newtonian theory, basically. So putting this to numbers, the accuracy of this framework for timekeeping is certainly better than 10 to minus 20. So all the applications like optical clocks, which will maybe fly in 10, 20 years to space, is covered with this in principle. But of course, nothing is forever. It should change in one way or another, but it is in very distant future. So if you look at these resolutions, you can have a feeling that two standard astronomical reference systems were defined. So barycentric celestial reference system and geocentric celestial system. And these two are defined in the mathematical language of general relativity by the form of the corresponding metric tensors first, and then additional to that, the four-dimensional coordinate time transformations between the barycentric celestial reference system and geocentric celestial reference system are explicitly written and discussed in the resolutions and in the corresponding publications. So we will come back to the first line here. These are these transformations, and the first line will be important further in this presentation. Actually, if you read the papers on this framework, you realize that actually we define not only two reference systems, but one reference system for a global reference system for the whole system of n bodies. And GCRS, so geocentric celestial reference system, is just a one particular application of the whole theory for the Earth. Basically, what we can do is to apply and should do, we should apply the same principles put forward in this framework to any other massive or massless body of in the solar system, moving somehow in the solar system. And this theory will give us a physically optimal, in certain theoretical and practical sense, a reference system for anybody in the solar system, massive or massless. So in this way, with exactly the same formulas, we can define lunar celestial reference system, or Mars, or the reference system for Mars, or for Mercury, and so on. So the same formulas work also for other bodies. Now, this time the IAU, certain commissions and other bodies proposed two resolutions for the IAU, and the resolution number 2 is the resolution which just say this: let us take the whole theory, which is well established, no flaws are known since more or less 35 years, and it is used for all practical applications for the known up to now, for all high accuracy models. So let us use it also for the moon first. And this resolution is actually has no alternative. So we have very good established theory, and it is very natural to use this theory also outside of the Earth for other bodies of the solar system. Now, in this talk, we would like to particularly discuss the coordinate time scale. I mean, the coordinate time for these additional reference systems for the moon and other bodies of the solar system. So the transformation always looks like this. And this is important to know and understand. This is a 4-dimensional transformation. So here you have, and what means 4-dimensional? It works only when you know where something happens, not only when you transform the time, but also where. So-called event in the language of the theory of relativity. So here you have everywhere the position, BCRS position, so barycentric position of the event, where you want to transform, say, TCB into TCG here, or it doesn't matter, TTB or TT or UTC can be here. It doesn't matter. This is very important to understand that we have these terms. If we ignore these terms, what would happen? Then we will destroy the simultaneity in the new reference system, in this local reference system, like GCRS, and then the Lorentz contraction effects and their gravitational counterparts would make very nasty effects, like the shape of the central body for the Earth or the Moon or Mars or whatever would vary depending on the barycentric velocity of the system of the body. This has nothing to do with any physical effects with the body. The body does not know how it moves actually, and it only depends on how we describe, and it would be a bad description. So actually the whole framework is aimed to avoid this sort of effects and avoids this very successfully. Okay, 4-dimensional. But these terms are easy to evaluate. What is not easy to evaluate in principle, these are these functions, these are post-Newtonian and post-Newtonian integrals. And there are a lot of publications, and now we have at least 3 publications on the market which evaluate these terms analytically for the moon. And now I would like to tell you that numerical computation of these terms is extremely simple. This is what we do for Gaia. We consider in the same framework Gaia as a body. It has exactly the same reference system. local reference system. And then here we can see that the body X, some body, it can be Gaia massless, it can be Moon, can be the Moon, Mars, or Mercury. And then this is the transformation at the center of mass of this body X between the TCB and the corresponding local reference system. Then the theory gives us something like this, what you see here. And then to the right of that, you see how it can be transformed. And then at the end, you get a very simple set of two ordinary differential equations with initial conditions. For example, as we do always for the coordinate timescales like this. And this is what we done, what we integrate very easily with arbitrary numerical integration using some background ephemeris. And then what you get, so I spent 1 hour, maybe 2 hours to compute this for different bodies of the solar system, for Mercury, Venus, the Earth, Moon, Mars, and Jupiter. And this is, so this is a full-scale time transformation between these time scales. And I used some particular numerical ephemeris from Paris and integrated for 60 years. So what you see, approximate linear drifts, very different for different bodies, and the amplitude of main periodic terms in this transformation also very different for different bodies. For example, for Mars and for Mercury, this is almost 10 times larger, these periodic terms, as for the Earth. Now, for this approximate linear drift, I remind you that there is no way, absolutely, to define the linear drift exactly. I remind you decades of passionate discussions on this topic for TDB, and the conclusion was you should pick up a number which makes sense. So, and this is what was done for TDB. So this would be also a possibility. Now, there is one freedom, basically freedom in all this framework, which was used for the Earth, namely to scale the coordinate times and other, but first the coordinate times. So this is an attempt to trick the physics, basically, to avoid the main effect of general relativity, which is the linear drift. And to define two coordinate systems, which basically has no, so TT first and TDB, which have no linear drift with respect to each other if you calculate them on the surface of the rotating geoid. So we have this TT, which is a scaled version of TCG, and TDB, which is a linearly in a different form, but it is also a scaled, linearly scaled version of TCB. This makes sense only for the Earth-related clocks, and the transformation is still four-dimensional, so you need all this. But the point is also that if you scale, if you really wish to scale, then you need to scale also spatial coordinates and also mass parameters, which enter the equations of motion. So these are the formulas, basically. Here you scale the time like this with some constant, and then you should scale spatial coordinates and also mass parameters. And also separately for barycentric and geocentric frame. And this is just to remind you and give you an example. Currently, we have 3 different masses for the Earth, mass parameters. Yeah, for TCB and TCG, these are the same mass. It is physical mass, and then we scale it, and then we have TT compatible and TDB compatible value of these masses. It is a mass by itself. But okay, now let us proceed. What to do with the other bodies? Now we have this resolution 3, which tells us, let us discuss it and decide later. This is basically what this resolution is about. Now, to scale or not to scale. One can imagine several scaling for other bodies like the Moon, Mars, and Mercury. The point is, when we decide relatively soon something for the Moon, this should really pave the way for the other applications like for Mars and Mercury. And now, whatever you do with the scaling, you have 3 aspects which are always mentioned here. First, do we have additional new values for mass parameters and special coordinates? So TX compatible. We have now 3, as I mentioned. Do we introduce more? Then the next question is if there is a linear drift of this scaled coordinate time for the Moon or Mars or Mercury with respect to TdB. The next question, if we introduce some analog of geoid on this body, if this scaled coordinate time has a linear drift with respect to the clock on that geoid, rotating geoid like solenoid or on Mars or Mercury, I don't know how to call them. And now different possibilities. First, you can scale in the same way as you scale TT. So with the same value. You introduce no new mass parameters and new scalings because TX compatible, so we call this scaled time TX. TX compatible is TT compatible. But you have linear drifts in both cases. Interestingly, in the literature, in this paper, I have seen another possibility. So the people for Mercury suggest to scale with the same value as for TdB. It looks like this. And then you again introduce no additional scaling, so mass parameters. TX compatible is TdB compatible. But you again have this scaling, linear drifts in the timescales. Now you can introduce the scaling with a special new factor to remove the main drift, linear drift with respect to TdB approximately. And then the good thing, you don't have at the center of the corresponding body the drift with respect to TdB, but you have new values for the parameters. So TX compatible for each body. And you have a linear drift of the clock on the corresponding geoid with respect to this timescale. Now you can remove this last linear drift with respect to the proper time on the corresponding geoid on the body. But you have again introduced new parameters, new scaled parameters, TX compatible, which are new for each body. And then you have significant drift with respect to TdB in this case anyway, because TdB is defined with the application for the Moon, for the Earth. And finally, my favorite case, don't scale at all. You keep the no additional values of mass parameters. You use the same physical parameters as with TCB or TCG. And you have these both scalings, both linear drifts with respect to TdB and with respect to the clocks on the corresponding geoid. That's it. So there is no way here to have more than one successes. All the rest will be, so the other two will be always negative. Now, this is my last slide. So resolution 2 is perfect. We define the lunar CRS as it should be. And I urge all of you to vote for this resolution. This is a very good thing. Then the coordinate times, the next story is the coordinate times scales in the solar system can be very easily computed by anyone to any accuracy, so numerical noise only, numerically and analyzed as well. Then there is no scaling of this lunar time scale, TCL, the new one, or for other bodies, which removes all linear drifts between relevant coordinate system, coordinate times. And not to forget, if we really want to introduce new ad hoc scalings, then we introduce one set of constants for each body additionally. And that is not a good thing. So I'm done. Thank you.
Okay. Thank you, Sergey. Questions from the audience? Questions? Okay, there you go.
You didn't use the word, but are we really talking about the choice of gauge in general relativity?
No, not at all, absolutely. The gauge is fixed. It is a harmonic gauge, and the gauge is fixed. We are talking about a affine transformation of coordinates, which are always allowed. Linear transformations.
Okay, thanks. Any other questions? Anything online? Okay. Nothing? Yes, we're going to move on to the next one. Thank you, Sergey.
Okay, thank you.
Okay. The next talk, the final one in our session before we're going to have a short discussion, is from Mark McLaren. He's here?
Hey, Susan, I'm here.
Okay.
I pre-recorded it for you guys if you want to play it.
Can we do that?
All right, can you guys hear me okay? Can I get a thumbs up or down if you guys can hear me or not? Okay. Well, hello everyone. My name is Mark McLernan. I work for the U.S. Geological Survey, and today I'm presenting some work we're completing for NASA on designing grid systems and map projections for navigation. So just a quick outline of what I'm speaking about. I just kind of want to introduce what Apollo has done in the past and what we're currently supporting for Artemis, what we're specifically designing, which is listed here, but just a quick brief on, map projections themselves and how they're formatted, and then we'll wrap up with conclusions and questions. So the primary motivation behind this work is the next moon landing for Artemis. And so I've just shown the 13 candidate landing sites here. Originally, when we started this work, we weren't really sure what was best and what was truly needed. A lot of the map projections designed for the moon are mostly done for open source mapping, and they don't really have the same level of, as a standard, such as Universal Transverse Mercator or Universal Polar Stereographic. So this is an old lunar map designed by the Army Mapping Service. And the reason why I pulled it aside specifically is it has this unique grid system. It's formatted with letters and numbers, and it's extremely condensed. And a lot of these old Apollo maps were kind of one-off gridding solutions where their position was unique to the mission. It changed pretty much during every Apollo mission, but they all have this same general format where it's highly condensed and it's kind of a hybrid of letters and numbers. And that's something that's been very desirable for mission activity going forward. The second map I want to show are these old Defense Mapping Agency maps. These are post-Apollo, so they were never used, but they're more terrestrial, and they are based on this old lunar transverse Mercator system, which was never really utilized. But if you just kind of look at the map grid itself, it's dimensioned in meters, there's eastings and northings, and in general, it's much more readable than the one before. And so the idea behind this work is, how do you combine the two? And how do you provide those same capabilities? So the requirements NASA has given me is basically build a grid system that's global in use case, limit the number of characters you can use to 6 characters to report a 10-meter area globally. They specified a scale error tolerance, and then they also wanted it to be designed in the mean Earth system, which is the current PDS standard. So this slide is just to reintroduce you to map projections, but basically these map projections we're using, they're transverse Mercator, polar stereographic. They're a way of converting angular coordinates in the current lunar, lunar reference sphere up to rectangular, so eastings and northings. Once they're converted, they're dimensioned in real space, and they're much more easier to navigate with. Just kind of one of the problems with having the landing sites so close to the pole is your directions kind of vary and distances change. You know, longitude change, the distance and longitude changes compared to latitude quite a bit. And so just having these map projections makes it more consistent and makes your directions and orientations more consistent. So our spin on this is basically to try and design something very similar to what's available on Earth. So we have a version of a lunar transverse Mercator system. It ranges from -82 to +82 degrees, and it has 45 zones in the North and South Pole for a total of 90 zones. There are false northings and false eastings applied, which is the first time in at least lunar mapping this has been done. And then the other specifications are here, just shown here on the left. We do have a lunar polar stereographic system. It has similar similar new values, including false eastings and northings. Use them in the polar values, so below -80 degrees and above 80 degrees. Here are the plots for that. So there is some overlap built in between the lunar transverse Mercator and lunar polar stereographic. It's a 2-degree overlap, so you can see those zones here. So you have basically your X zones in the north and then your C zones in the south. And again, it's designed very, very similar to universal polar stereographic. And so you've seen this slide before. This is the same slide as the lunar transverse Mercator. I've just put it here just so you can kind of see this transition to the grid system. So built on these two systems, if we just review lunar transverse Mercator and lunar polar stereographic, we start out, we apply a lunar grid system. And so the coarsest resolution of this is kind of global in scale. It places these letters down. So each one of these square areas is 8 by 8 degrees. And then we have extended zones, which are 8 by 10 degrees in the north and south. So those are your C and X zones. So this is kind of your coarsest level. The next size down is a 25-kilometer grid. And so this is not the best way to display this. So I have polar plots available on the next slide. But it's very similar to the military grid reference system, where we label things alphabetically to specify a grid area. And in our case, we went with a 25-kilometer grid area. It seemed to work best for the moon, just given the size difference between Earth and the moon. So here's basically how it's labeled equatorially for every single zone. You'll feel free to ask questions on this later or come back to this. Here they are. So here's the same polar stereographic slides. Here are the global resolutions. So A and B are reserved for the South Pole, and then Y and Z for the North Pole. And again, you can see that overlap. And then here's the 25-kilometer grid zone. So these aren't randomly labeled. They're labeled alphabetically, so you can basically see A counts down alphabetically going to the east, and then it counts up from Z going west. This was deliberate to force a direction, and then it just counts down alphabetically, A to Z going to the north. So again, these are 25-kilometer grid zones applied to the moon. It's very similar to the military grid reference system. So you can specify your coordinate position when navigating globally. So kind of coming back to some of the original requirements from this, as I mentioned, there's a 6-character requirement. This has been specified by Johnson Space Center to limit the cognitive impact to their astronauts. I'm sure just navigating on a different celestial body in completely unique terrain has its own challenges combined with all the mission activity they'll be doing. So minimizing cognitive impact is a high priority. So basically, again, we have angular coordinates, we have our map projection coordinates, in this case, lunar polar stereographic, that converts over to a grid coordinate. And then once we have this grid coordinate, it can be condensed down. And so that's the idea. Something we've kind of coined is called Artemis condensed coordinates. And it's a relative coordinate to report your position. So you can see these coordinates on the left. Just to break it down here, you have your polar zone, you have your 25-kilometer grid area. Then after that, you take these easting and northings from the grid system, and then you condense them down. So we take tens of thousands and thousands of meters, and we assign a letter to them. And then because we only need to report position to 10 meters, we drop the ones position. And so because it...
1 minute?
Thanks. Because it's relative, you know your position within this 25-kilometer area. So here's an example of Apollo 17. These are LGRS coordinates. Here's the 25-kilometer grid zone on the left. And then after that, you're down to your condensed coordinates, where you have basically your 1 kilometer grid, and then you're down to tens and then single meters. So this research station here on Apollo 17 is just defined by the single coordinate here. And if you need the 6 characters, you just report these characters here. So that is my talk. Thank you so much for bearing with me, and thank you for hosting this as well.
Okay, really quick. We have time for one quick question for Mark. Yes.
Thanks for that. I'm just wondering how you define the prime meridian.
Yeah, so right now the prime meridian is 0. It's defined on the mean Earth system, so it's 0 degrees facing Earth.
Okay.
Sorry, when what is facing Earth?
So
the center, basically the bisector of the circle as we're looking from Earth. Is that it?
Let me see here. Yeah, so we define the primary. So currently, 0 degrees longitude on the moon is our prime meridian.
Okay.
So we're not really. Oh, go ahead, Susan.
Go ahead, finish your thought.
That's okay. Yeah, we're not really defining anything too new with this. We're just building these grids onto what's already currently available.
Okay. All right. Well, thank you for joining us. We're going to postpone the discussion we're planning to have until the next session, because we don't want to keep any more time between you and the coffee break. And we're going to start up here again at 3:30. What? 3:30, 3:30. Thank you all for joining us.
Maybe
here to chair and yeah, we wait a few more seconds. People are still joining the session. Usually take time, and we were also late for having the coffee. Did you get a coffee, Susan? No, you should have asked me. I just so maybe we can start slowly the last session of the division days for Division A. Just some forwards. Bonnie Steves excuses herself. She would have been the chairman of this last session, and Bonnie Steves will be the next president of Division A. But she couldn't make it to come eventually, and not even online. And so we have some session about working groups reports and commission reports, in addition to some of a business meeting that can be held during the General Assembly. But it was also good to have their report here today in front of everyone. So some online, some here in presence, and maybe an announcement before we start the reporting. So there will be some announcement during the reports, but there is also the focus meeting 11 on multi-wavelength astrometry that was supported, coordinated by Division A, that will start on Thursday, Friday, Wednesday, Thursday in this room. Okay, so that's after the Division A, you can go to the focus meeting 11, and we start so with some working group report, functional working group. The first one by Tony Almott.
Hello, I'm Tony. Apologies, I've got a bit of a cold, so if I sound a bit croaky, that's why. I'm going to be giving a report on Standards of Fundamental Astronomy, otherwise known as SOFA. So what is SOFA? We provide a software collection that provides an authoritative set of algorithms and procedures that implement standard models used in fundamental astronomy. And we're a functional working group of Division A. Our material we provide is available via our website, iausofa.org, which you can see a bit of an example of that later. The software is available in both Fortran 77 and ANSI-C. The first release of our software collection was released in 2001, and this was Fortran only. The first version to have a C version was the 6th release, which was in 2009. So until that point, it was only available in Fortran. There have been 19 releases in total, 19 major releases with some minor releases in between. And the latest release, release 19, was made available on the 11th of October, 2023. Now, anyone can use the SOFA software free of charge. So that's just a clip of our website with the latest release on there with the QR code, which should take you to the website. So the SOFA is managed through an international panel, which is known as the SOFA board. And there's a few of the names on there, including Steve Bell, who's actually with me here today. There have been a few changes to the SOFA board this year. One notable things is that Catherine Hohenkirk was the previous chair, has stepped down, and I was appointed in her place. We've also had 3 members of the board step down this year, so we thank them for the service they've given. So what's available? We provide 2 source libraries of routines, again in Fortran 77 and ANSI C. So this material is available for most operating systems via tarballs and zip files, and individual routines can be downloaded from our website. There's an archive of previous releases, so you can download any version of the software, old and new. It includes Unix makefiles to use to build the libraries, and there's validation programs for both the Fortran and the C. We also include some documentation and cookbooks, which I'll talk a little bit more later. And in total, there are 247 routines, 192 astronomy, and 55 vector matrix routines. So documentation, there's the SOFA manual, which is included with all the releases. There's also the astrometry tools at a glance, which is a 2-page quick look document. And then we have 5 cookbooks, the tools for Earth attitude, timescales and calendar tools, astrometry tools, vector matrix library, and miscellaneous topics, all of them available in PDF form from the website. So the routines are broken down into a number of categories. Some of them are listed on there at the moment. And you can see roughly how many are in each of the different categories. There's some more there. So as I mentioned earlier, anyone can use the SOFA collection for free. However, there's some licensing information that's important to read. This licensing information is provided in every SOFA routine, so it should be quite easy to find this information. Our routines are read-only, apart from the leap second routine, which is the only exception. This is classed as user replaceable and has a licensing statement which permits distribution of local variants under the same name. So you can make changes to the code. However, if you do this, you have to say so and not claim that it's still a SOFA product. Again, apart from with the leap second routine. And we do kindly ask that if you do use the software, please acknowledge SOFA. So since the last General Assembly in Busan, there's been 1 major release. This had some corrections and improvements to several of the routines. We also released a new cookbook on miscellaneous topics, which was about ecliptic and galactic coordinates, the transformations, geodesy, and solar system ephemerides. We also made some enhancements to existing cookbooks, the astrometry and Earth attitude. So some statistics of the usage. We have about 1,050 registered users at the moment. We have an average monthly visit of about 1,550. This was in the period of 2021 to 2024. We can't give too much detail about who these users are at the moment because of the way our website acquires the hits. So that sort of is general statistics only. So the number of downloads for release 19 for both Fortran and C were about 2,350. And about 70% of that was for C, with 30% being for Fortran. About 75% of our users express an interest in both versions, 6% for just Fortran, and 19% for C only. There are some other implementations of SOFA which are supported independently of our libraries, but are derived from it. There's the Java version from the Java Bank Center, the Essential Routines of Fundamental Astronomy, which is a rebranded ANSI C version from AstroPy, and the Worldwide Astronomy C# library. So if you'd like to download SOFA, again, there's the link to our website. Please register to receive updates and information on corrections and new releases. Again, please could you acknowledge the use of SOFA if you are using it? And we would like to thank the board members' institutions for their support and the UK Hydrographic Office for hosting the website. And thanks to the users. If anyone would be interested in joining the SOFA board, please feel free to speak to me about this. Thank you very much.
I see some questions, and in the meantime, maybe I can say, as you said, that Tony is the new chairwoman of this working group, and so she was elected. And welcome. Thank you for taking the chairing after Kathleen Holler.
Oh, very short question. Any plan for Python version? Because more and more young people are turning to the Python, yeah.
Sorry? Oh, Python. That's something we could definitely discuss with the SOFA board.
Just to comment on that, sorry, I'm Eric Tyler at Space Telescope. I'm one of the people that did IRFA. So IRFA is essentially, has a Python layer wrapping around it that is essentially, I think, exactly what you're looking for. So I was going to comment that your user level of 1,000 or so, I think you can multiply that by 10 because that's the AstroPy user base, and AstroPy wouldn't work without SOFA by way of IRFA. So I think you're lowballing your usage by a wide margin. I just want to say that. But I also wanted to ask if, and there isn't one of these yet. There's been this push by certain government agencies to push towards memory-safe languages, which, whatever you think about it, what they really mean is Rust. Has there been any thought to put into turning, building also a Rust version, because this is, at least in some circles, that's probably the way of the future as mandated by government officials?
There's been no discussion about that so far, but with the ever-changing world, it's definitely something to talk about. It's just because these versions have been available historically doesn't mean that we're limited to them in the future. Okay.
There is an online question.
So far, always avoid using external files. Will this continue? About the usage of external files, this is avoided by SOFA, and someone is asking if it's will this continue?
I believe so, yes.
Okay. So thank you again.
Thank you.
Yes, and the next report is online by Felicitas Arias. The time metrology standard, and plus additional time to a note on the evolution towards continuous UTC. Felicitas, I see you. Can you
hear me?
We hear you. Can you share your slide?
Yes, but I don't have the authorization. So I need to
wait a second
to share my screen. That's right.
It's coming. It's okay.
Good. So I will present one.
Oh, wait. No, wait. Are you sharing? Okay, well, yes. I see. It's in French, so it's your computer we see.
Yes, it's in French. Let me do something because now.
Okay. That's the one. Control L, no, that's not the.
Yeah. So.
No, wait. It's black.
Is it black? Just wait a little bit. I will do it again.
Perfect. It works.
Okay.
Parfait.
Okay,
go ahead.
So I will do one presentation after the other, so this will save time, and then we can have questions at the very end if it's okay. So I will start by the report of the working group on time metrology standards. And to begin with, I would like to explain that time is the result of coordinated activities between different organizations. So the IAU is one of these organizations, but it is not the one who is defining and realizing the practical timescale, which is in the hands of international metrology. So there is a need of a strong link between the astronomers and the time and frequency community. So there are intergovernmental organizations that are dealing with those definitions and realizations, and there are mainly two: the General Conference on Weights and Measures, that is the Meter Convention, that defines units and references, and in particular the unit of time and the reference time scale. There is the executive organ of the CGPM, which is the Bureau International des Poids et Mesures, that realizes and maintains the time scales, TAI and UTC, in cooperation with time laboratories. And then there is the International Telecommunication Union that is charged to do everything to disseminate time and frequency signals. And among all these activities, there are recommendations, and one recommendation that is interesting for astronomers, which is the one that says how to synchronize more or less UTC to UT1. And then there is the IRS that is providing continuously the values of UTC minus UT1, and that informs when leap sequences are implemented. So it is clear that there is a need to have a link to time metrology standards from the IAU. So this working group has this objective to link with this community. And we have a membership where we have astronomers, we have scientists working on time and frequency metrology, and then we have mixed, those that, as is my case, are working on both sides. And the distribution is in the membership of 18 people, we have about 50% of pure, let's say, astronomers, and then the other 50% has an equal, more or less, repartition between these mixed scientists and time and frequency metrologists. I've been chairing the working group until now, since it was established in 2015. And now the working group will go to the hands of Frédéric Ménadier from the BIPM and Gérard Petit, who retired from the BIPM. So in this link to time and frequency metrology, we are interested in the hot topics that the Consultative Committee for Time and Frequency defined several years ago. So one of the hot topics concerns UTC, and it is the work towards making UTC a continuous time scale. And we had activities on this direction. I will explain more in the second part. So now I will just say that our working group contributed to the work of the Working Party 7A of the International Telecommunication Union, which had the mandate of preparing a report to be presented to a World Radio Conference. And we had the input from this working group to that report. So we provided a text saying which is the impact on astronomy of any change in the present UTC system, the advantages and disadvantages of having a continuous or a stepped UTC. And then we said some words about the measures and the time period that astronomers would need to implement changes. Another hot topic of the CCTF, without action from the working group, but just being aware of what's going on, is the redefinition of the second, of the unit of time of the International System of Units. As you know, until now, the second is defined by a microwave transition, which is the cesium. and work is progressing towards a new definition, which will be accurate in 2 orders of magnitude better than cesium, and that by the moment, all these transitions laboratories are working on are considered secondary representations of the second, because the primary is cesium. But the General Conference on Weights and Measures started working on that, of course, with the input of the Consultative Committee for Time and Frequency, and they established a roadmap that will go, hopefully, until a little farther than 2030, where the decision on which of the species laboratories are working on will be selected, if there is one, or if the second will be defined through a combination of transitions. This is a point they need to discuss, plus some important adjustments, such as having a number of laboratories comparing their optical clocks and having contribution to UTC from those optical clocks. So we can expect that a new definition of the second will arrive after 2030, very close to 2030. This will not have a direct impact on astronomy work, but of course will improve the accuracy of the timescale. Then we had some activities on the time reference in cislunar space. We established a working group on lunar timescale within our working group last summer to exchange ideas and discuss on the topic, and we appointed a member as the contact person in Commission 3. We supported the proposal of the IAU Symposium 401, which is advancing reference systems, ephemeris, and standards, and this will go from the Earth and the Moon to solar system bodies. As Susan explained, this symposium will be in La Plata, Argentina next August. Our working group was a supporting body. We are in the scientific organizing committee. We have 2 members, Mizuhiko Ozokawa from Japan and myself from France. And we will have a nice session on time with a plenary talk by Noël Dimarc, the president of the CCTF, and Patricia Tabella, the director of the BIPM Time Department, on the challenges of time metrology. And we will have invited speakers to talk about UTC and the work on UTC, Joseph Ashkar. Pascal Defraigne from Belgium will talk about lunar time, and Tetsuya Ide from Japan will present standards for the redefinition of the second. Then there will be future actions, and the new chairs will be charged of that. We need to revise the membership of the working group. Some people retired, so we need to make some refreshment. We will continue the interaction with Working Party 7A of the ITU on the issues on UTC, because it continues. We will provide the IAU with updated information on those hot topics of time and frequency metrology, and we plan to contribute, of course, to the future discussions on the time standard for the Moon with the IAU bodies. So with this, I will conclude the report of the working group, and I will go to the evolution of UTC towards a continuous time scale. I must say that when this discussion started at this was in year 2000, the idea was to stop inserting leap seconds in UTC. So the issue was called the leap second issue. So there has been a move towards the idea of increasing the tolerance, increasing the maximum value of UT1 minus UTC, for a long term instead of saying we stop inserting leap seconds. And I go back to one of the previous slides I showed during the report, because it presents clearly where things are happening. On one hand, we have the General Conference on Weight and Measures, which have meetings every 4 years and makes resolutions. So these resolutions concern units and the unit of time and the time scale which has this unit. And then we have the International Telecommunication Union, which has also conferences, and these World Radio conferences make decisions and take resolutions also concerning the way, in our case, time and frequency signals are disseminated. I want to note that these are intergovernmental organizations, differently from IAU and from IRS, which are scientific organizations. Why this discussion on UTC is in these two organizations, mainly ITU and CGPM, is because there are member states, administrations are voting. We don't have scientists voting. We have administrations. So these administrations ratify agreements within a treaty. And this is the very strong point of doing this in these organizations. Then scientific bodies will organize matters which are different, which is the case of the IAU, where we define coordinate systems in Earth and space, transformations, and we defined the dynamical time scales, but we are concerned with the relation between the practical, the international time scale UTC and UT1, because it is necessary for astronomers. And then we use, of course, the information from the IRS. So if you look to this slide, you will find on the left-hand side the evolution of the difference of UT1 minus UTC stepped since 1972 with these 1 second steps from time to time. And if you look to this plot, you will see that since a while, since 2016, things are happening differently. The rotation of the Earth is behaving differently to the point that we have not applied very frequency leap second steps, and that since a few years there is a change in the trend, and that we could be faced to apply for the first time a negative leap second, and of course we don't know what this will be. Then if we look to the second plot, the plot on the right, you find the difference between UT1 minus TAI, UTC minus TAI. You see the steps and the 37 seconds difference between TAI and UTC, from which 27 have been applied since 1972. So this is the process as applied today, which results not really convenient for many applications. So let's see the chronology and we will come to the end. In year 2000, the discussion started, and it was at the ITUR, and it was very active with the BIPM and with the CCTF. In 2015, the ITU made the World Radio Conference and put a resolution that says, okay, international organizations should work strongly and together with the ITU. From this cooperation, it is necessary to know which is the value of getting UTC as it is, or of changing UTC, and knowing which is the impact on applications. And then they ask tell us something about how we could disseminate a new form of UTC and prepare reports to make us aware of what is happening. And we will work about that in the next World Radio Conference. In fact, they gave us 2 periods, the World Radio Conference 2023. And in the middle of that, there was progress, and the CGPM put a very important resolution that clarified who is doing what, who is responsible for what. In that resolution of the CGPM, there is a clarification on what is the CGPM and the BIPM responsible for, and what is the ITU responsible for. And then there is a clear definition, a metrological definition of TAI and UTC, which is supported on the IAU resolutions 1991 and 2000. 2020, a big step. The BIPM and the ITU signed a memo of understanding, and this is for working together on this issue. And 2022, we put this report, the report which is numbered 2511, in response to the World Radio Conference, where the IEU, through the Working Group on Time Metrology Standards, say words on what is the impact on astronomy. And in 222, the very big step was done. The CGPM adopted a resolution which is called on the future development, on the use and future development of UTC. And the important thing is that it was decided and approved that the maximum value for the difference UT1 minus UTC will be increased, and that this will happen in 2035 or maybe before, that this step should be no less than 100 seconds. It seems in the discussion that it could be 255 seconds. And this is done to be sure that UTC will remain continuous without steps, at least for 1 century. So now the second step will come in 2026, when the CGPM will say the final word. In the meantime, the World Radio Conference, the ITU, revised that resolution that said work together. Yes.
Can you conclude, please?
Yeah, and put a report. And the new resolution says you need to continue studying, and important thing, you need to tell us how you will disseminate UTC when you will get rid for a century of the leap second. So what will come next? The CGPM needs to make a decision in 2026. The numbers will be given, which will be the maximum value of UT1 minus UTC, and when the change will be adopted. And in this work, there is a group preparing this resolution, and the IAU is in this group represented by Dennis McCarthy. And then at the Working Party 7A, on the side of the ITUR, we are working on 2 preliminary draft reports, one that will say how the different systems of dissemination, either radio communication or wire technologies, will disseminate UTC in a new form. The codes that were used when we stepped 1 second will no more be useful. And we will also propose a revision of the recommendation that says that we need to synchronize the timescales by leap second steps. And of course, these works are and will be conducted in cooperation with all organizations and the ITU sectors. So this is the end of my report.
Thank you, Felicitas. I think unless there is a very urgent question, we move on to the next speaker that is also online. Brent Archinal for the working group on cartographic coordinates rotational element.
Yes, okay. Can you hear me and see the slides okay?
Yeah, perfect. 10 minutes.
Okay, good. Okay, so I'd like to make a presentation here, an update on the current work of the IAU Working Group on Cartographic Coordinates and Rotational Elements, the Division A and F Working Group, and certainly like to acknowledge my co-authors, the members of the working group that are listed in a later slide. So we'll go ahead, if I can get the slides to advance here, to general outline here the topics, the recent activities of the working group, changes we hope to make in the next main report that we do, information on the lunar reference frame, and seeking input on the evolution of the working group, and certainly are open to input and discussion to all of that. The working group itself has as its main goal promoting the use of a standardized set of mapping parameters for solar system bodies. We make recommendations, always open to modification when needed, but intended to facilitate the use and comparison of multiple data sets. And we do this by issuing reports with the recommendations about coordinate systems and related parameters, with these recommendations being updated as the accuracy and precision of data improves and as the accuracy and precision of the coordinate systems improve. The working group itself was founded in 1976. It's been an IAU functional working group since 2016. Starting in 1979, these reports have come out about every 3 to 6 years. Our current report was published in 2018. An image is at the center, and these are available from our website as shown in the image on the right. So as to the operation of the working group, we are open to membership like probably all IAU working groups by invitation or volunteering. We currently have the 15 members listed here from 5 countries, anywhere from 6 to 48 years of membership, including one of our original members. We look at newly published coordinate system determinations and referee journal papers. We recommend standards based on those and based on our consensus among us and input from others. We don't have any independent resources of our own to do this work. There's no external funding. This is all volunteer, and we don't bless or enforce these recommendations in any way. We just provide them, and their value is in the validity and their consistency and the reflection of general consensus and input and use from others. The recommendations are primarily for mapping, but other uses are quite common. Example related to dynamical systems or navigation. We don't deal with formats or lower level mapping standards in this process. So as to recent activities, we did spend a few years and are still at a low level continuing doing presentations, asking for input to the working group. There's a list of the presentations here and a white paper that we submitted to the NASA decadal survey about this. But mainly we're looking for input on how we make recommendations and the future of the working group. We haven't been particularly successful at getting a lot of input, especially early on due to the nature of virtual meetings, but we may try to do surveys and try other methods of collecting input. For the last couple of years, we've also done presentations and provided a lot of information to various users and groups on the lunar reference frame. We're continuing to create annual and triennial reports to Division A and F, and those are available on the IAU web pages, and they list all of our publications and presentations, of course. We're always seeking new members for the working group. We just completed a new members packet that explains more how we operate and what we do, and we're inviting any interested people to join the working group. So further volunteers are welcome. Our next main report has been long delayed, but we're hoping to start into that in a expeditious way soon. We've had delays due to the usual things, the pandemic, workload, helping about the issues related to the lunar reference frame and so on. As to the content, the next slide here has some of the main changes we probably will be making, possibly an update to the lunar reference frame, probably an update to the Mars reference frame and orientation model, because in the last go around, there was accidentally a 100-meter offset introduced in the longitude for Mars, while the longitude for Mars was established connected to the Viking 1 lander. We probably will do updates due to new results from many missions throughout the solar system over the last 10 years, and updates based on terrestrial mapping of asteroids with very large telescopes. As part of what we do, we'll also describe the assistance we provide on coordinate systems and mapping issues, particularly to journal editors, helping review papers and answering questions. But we're aiming to try to get something out in early 2025. Just one slide here on the lunar reference frame, and many of you have just heard my presentation in the last session, so some of this is repetitive, but just as an overview, there are, of course, the mean Earth polar axis systems and frames and principal axis systems and frames. The current recommended system actually came from the NASA Lunar Geodesy Cartography Working Group using international input in 2008, recommending the use of the JPL ME421 frame and ephemerides. And the working group echoed those recommendations in its 2011 and 2018 reports. And essentially all lunar data since that time is in that frame from all nations, all space agencies, all missions, at least for mapping the surface of the moon. So the question is, should it be improved? And various NASA groups and others have recommended changes because we now have solutions that include more data, better modeling, better accuracy for the frame internally. And the critical function, though, is to maintain, as I mentioned in my last presentation, the coordinates of surface features. So this is not a new ME frame from first principles, but a cartographic frame. And a solution to this is, as I mentioned before, the JPL ME440 frame, which provides an update but matches the orientation of the previous frame. And it's been raised that should PA be used instead of ME for mapping and navigation. And since there's a large up to 875 meter offset between the frames, such a change would likely cause substantial confusion and high costs for conversion of data and map products. So any goal and advantage of such a change is not entirely clear. So again, feedback is welcome to the working group. As the working group itself, it's been in operation now for 48 years. We have considered issues and accumulated experience over all those years of operation. We do try to cooperate with other groups. You can see a sort of a partial list here on the right of groups that do things related to planetary coordinates. But what type of coordination is really needed through all these different types of international and other organizations? We discussed this somewhat in our 2020 white paper submitted to the decadal survey. Another part of this is, what about the working group itself? How does the working group continue? How should it continue? We could just continue on in expanded form with additional personnel and resources, perhaps with space agencies contributing to this because of the importance of the work. We could supplement this working group with other working groups that provide lower level or specific body recommendations. Maybe there are planetary spatial data infrastructure groups that could contribute to this. Another option is to create some sort of service similar to the International Earth Rotation and Reference System Service, with some of the details of it described on the right. But there could be components for cartography and standards, oversight by some board or the working group itself. There could be dedicated staff to help with this. And it is certainly obvious that the work that the IRS does may be much greater in terms of perhaps data volume and geodetic methods for the Earth. But the working group actually handles not just one, but 97 different solar system bodies, and more coming, of course. So I'll end here just by saying we have done these annual and triennial reports that list our efforts and our publications, and you can find those on the IAU website. Our most recent reports available on our separate USGS-related website, and along with previous reports. And the decadal surveys available from comments are available from the NASA website. So again, input is welcome. You can see my email address and the website location at the bottom here. And we're going to hear a talk in a little while from Alberto Escapa, so I won't say a lot more, but certainly want to advertise the IAU Symposium 401, Advancing Reference Systems, Ephemeris, and Standards, which this working group, of course, also supports. So thanks for your attention.
Thank you, Brent. Is there an urgent question? Comment? So thank you again, Brent, and we can move on to the next report by Anatoly Ivantsov for the ground-based astrometry. By small telescope, sorry. Hello, Anatoly.
Good afternoon, dear colleagues. It's my pleasure to give a view of, on the triennial report of our working group, Astrometry by Small Ground-Based Telescopes. I have provided here a short list of authors, but of course, these are the members of our working group that communicated us our reports. So, I will remind you about the purpose of our working group. It was to update and maintain information on astrometric programs, to facilitate astrometric measurements of both small solar system bodies and also stellar objects, and to facilitate the collaborations to help for the coordination of the activities in astrometry from ground-based telescopes. At present, the working group comprises of 24 members. For the past period, I will make just a brief description of the communication given to the working group. Jean Darlot from Paris Observatory has reported about a worldwide campaign of observation of the mutual events of the Galilean satellites. There were observed 85 phenomena by 37 observers from 18 different sites. And on the second point, he has mentioned about the digitizing project of photographic plates that is ongoing at Paris Observatory. And the new reduction will be made with the Gaia catalog. Marcelo Safin and Roberto Vieira Martins from Brazil have reported about observations at two telescopes, 60 centimeters and 1.6 meter telescopes for observing small solar system bodies. As well, they have observed natural satellites, and they have done astrometry of Jupiter irregular satellites. And 5 mutual events of the Galilean satellites were observed as well at the Observatory do Pico dos Dias. Goran Damljanovic from Astronomical Observatory in Belgrade has reported about observations of double and multiple stars and also extragalactic radio sources, objects for Gaia astrometry and photometry at 2-meter Rogen telescope in Bulgaria. As well, he was engaged in observations of Gaia-alert objects, whole Earth Blazar telescope objects, and double and multiple stars using the lucky imaging technique. Francois Tari from Paris Observatory has reported about the Elixir project, that is further development of robotic telescopes located in French Alps and in Haute-Provence. He has pointed some instrumental advances to be completed in December of the past year. The first light will appear this summer, and they expect to have about 1.25 petabytes of data for every 5 years. Charlie Thomas Finch from the United States Naval Observatory reported about astrometric and photometric observations taken with the Deep South telescope, with a great number of exposure, more than 10,000 taken in 2021, and more than almost 18,000 taken in 2022 to monitor a selected list of extragalactic celestial reference frame sources. And as well, there was implementing a bright star photometry program on the optical arm of the mentioned telescope, so that it will be useful in future to have photometric characterization and monitoring for the bright infrared objects. And William Tuilot from Paris Observatory has reported about follow-up program focused on monitoring Gaia alerts for solar system objects. More than 500 small solar system objects were observed, either newly detected or with imprecise orbit, and their positions were submitted to the IAU Minor Planet Center. And this network comprises of the number of telescopes listed here. As well, I would like to point your attention that our working group supported and also were among the organizers of the IAU Focus Meeting 10, Synergy of Small Telescopes and Large Satellites for Solar System and Exoplanetary Bodies Research, held at the 31st General Assembly in Republic of Korea. We consider it to be quite successful. There were 49 talks communicated to the participants from 27 countries within 2 days. And as brief conclusions, I would like to say that small telescope with diameters less than 2 meters are still useful for getting accurate astrometric measurements of bright smaller system bodies, natural satellites, either through direct imaging or using photometric measurements of mutual events. As well, follow-up networks, observational campaigns that are using small telescope have advantage due to extension of their observational sites in longitude and latitude that increases chances of getting clear sky necessary for successful monitoring of the objects of interest. And also, I would like to point your attention that the working group facilitates sharing of information and experience, coordination of campaigns, and setup of telescope networks. And also, we invite the groups and also individual astronomers to communicate us through email or by mail to probably to have share and also to probably to help or assistance of us in astrometry of high quality. I would like to invite you to visit our webpage that is given here. Thank you very much for your attention.
Thank you. Any questions? Okay, so we can go to the next speaker and I give the microphone back to.
Okay. Then Chris, I guess that.
Okay. You have to hit it to get the first one. Did the slides get loaded? Here we go. Hi, I'm Chris Jacobs. I'm the chair of Commission A1 on Astrometry. I'll keep this short because we have a 2-day focus meeting on Wednesday and Thursday. We have 44 presenters, so for those that want detail, there'll be plenty of detail. Okay, where'd it go?
Yeah. Okay. As I think most people in this room know, astrometry is about measuring positions, parallax, and proper motions or velocities of objects in space. We measure orbits of planets, binary stars, galaxy mergers. We build reference frames, and we support navigation. I'll briefly review the current officers, and at this meeting, we're transitioning to the next triennium and the new officers. Our membership, we have 208 people total. And as I said, we have 44 presenters in our focus meeting. So we've got a very active group. Our focus meeting is going to focus on multi-wavelength. We have work going on in the radio, millimeter, submillimeter, infrared, and optical, both ground and space platforms. We do imaging, interferometry, Doppler velocity, so a variety of data types. And there's the details. This room is where the focus meeting will be on Wednesday, and it's down the hall on Thursday. Here's our current officers. I've been the president. Aletha de Wit from South Africa is the vice president. She'll rotate up to being the president. She'll be at the focus meeting if you want to go meet her. It's kind of a happy coincidence that we have an African at this meeting taking over, and she's now in charge of radio astronomy for the Department of Science and Innovation here. So she's got quite a bit of reach, and she's a good point of contact for that. And then Patrick Charlot. Patrick, you want to raise your hand? He's the chair of the multi-waveband International Celestial Reference Frame. He'll be giving an overview talk, an invited talk at the focus meeting, and he's the guy to talk to about the ICRF. Here's our new officers. As I mentioned, Aletha de Wit from South Africa is the president. David Hobbs, who's been championing a next generation Gaia, will be the vice president, and I'll stay on as advisor. And then we have some second term officers, and Megan Johnson and Hannah Krasna are our new people. In the optical, space-based Gaia, as you mostly know, is up to 1.8 billion objects, just an incredible number. We have some ground-based large surveys, optical and near UV. We heard some talks about Vera Rubin, ground-based interferometry. The VLTI and gravity has kind of come of age with ground-based optical interferometry. In the infrared, we have the next generation space images, the Gaia Near IR, the Japanese Jasmine mission. In the submillimeter, the Event Horizon Telescope people are taking VLBI up above 230 gigahertz, unimaginable from the days when I was starting. And in the radio, we have centimeter, millimeter, and submillimeter. The ICRF, the International Celestial Reference Frame, has existing components at 3.6 centimeters, 1.2 centimeters, and 0.9 centimeters, and then Gaia Optical, which was also blessed by the IAU in 2021. We have a couple candidates for the ICRF4. Vigos, which is a VLBI frame at 3 to 10 centimeters, is starting to produce astrometry. It's not yet full sky, so we'll see if they get full sky coverage before the next meeting. Q-band, 0.7 centimeters, the same thing. We have coverage from the North Pole down to minus 45. They're looking to get full sky coverage and become a candidate. Differential VLBI for parallaxes, proper motions, for example, Bessel mission. That technology has just gotten to amazing levels. They're getting several microarc second kind of precision, 510 microarc second precision. And then where I'm at JPL, we're using astrometry for spacecraft navigation. Upcoming milestones, the Gaia Data Release 4 is conservatively listed as not before mid-2026. There's a little cartoon of all the amazing things they've done, the number of objects and the number of transits, and a list of all the things they're doing. The ICRF, multi-wavelength ICRF, we're aiming for August 2027 to present it to the IAU in Rome, and it will have Gaia and multiple radio frequencies. And our focus meeting, I'll just briefly go over it. It'll start Wednesday at 10:30, and we'll have poster sessions. The posters will be up for the full 2 days, so you can browse those. The first 2 sessions will be on celestial frames, mostly radio. Session 3 and 4 on Gaia and Gaia sources, binaries, characterizing sources, some details of optical interferometry. Session 5 will be developing instruments and methods, next generation differential VLBI. The Koreans have a new multi-band system. JPL's got a broadband system, next generation VLA. There's a VLBA upgrade. So it's really a very active time in the world of astrometry. And our final session will be future missions and telescopes. I mentioned Gaia Near IR. That's the Gaia follow-on that we're trying to get going. Jasmine from the Japanese, the sub-millimeter next-gen EHT. And here in Africa, there's the Africa Millimeter Telescope, and there's a proposal for a millimeter telescope in Kenya. And the full program is listed there at that website, and it's also linked to the main IAU website. So that's about it. If there's any questions.
No questions, or see you on Wednesday in this room. Is it you now? Okay, I'm the president of incoming president of Commission A2. Give me the report. Thank you, Alberto Escapa.
Okay, thank you. Well, please start the timer, please. Thank you. Well, the first part of the presentation is just some report of the activities of A2 Commission, rotation of the Earth, on behalf also of the current president, Sinobi Malki. Well, our commission is very old as the International Astronomical Union. We were one of the founding commissions, and as its name, it's more interesting, the slide.
We are putting the presentation
on. Okay.
It's okay.
Okay. Yes. We are on the right. So we have a long history. Our aim is working on Earth rotation from all the points of view, theory, observation, analysis, and in this field, it is important to keep coordination with other international organizations like IEG, IERS, IBS, and others. We have passes on different names and different denominations inside of IAU, variation of latitude, Commission 19, and now Commission A2 and rotation of the Earth. And we have, we have, that is all our history. There is a nice paper by Sinobi Malkin with the history of the commission, and you can see all the presidents there. And just being here in South Africa, the second one was Sir Harold Spencer Jones. And well, it was a very important guy in his epoch. And one detail is that, of course, in addition to president of the IAU, he was also president of our commission in that time variation of latitude, and he made a big promotion for the development of astronomy in South Africa, since he was here the astronomer of the observatory at the Cape of Good Hope, and also president of the Astronomical Society of Southern Africa. It is in the Earth rotation field, it works on the variations on the rotation speed and establishing some research saying that the Earth was not a perfect timekeeper. By some accident, his predecessor here in the observatory was Hugh, that was also a very important guy for Earth rotation studies, because he was the first formulating a two-layer Earth model describing the oscillations of a rigid ellipsoid with a fluid core inside. That was made by Hugh, and also an astronomer here in Cape Town. Okay. Well, the objectives of our commission are described here and also on the web. We have, as I mentioned previously, one part of cooperation with several organizations, and a link between the terrestrial and celestial reference frame and systems, and the third ingredient that are the Earth orientation parameters, develop methods for improving the accuracy and understanding Earth orientation variations. One important point is to get continuity of the reference frame across all the changes, and also to fostering observational and analysis methods, and also new observation techniques. We have now 114 members, so if you are interested in Earth rotation, you can join us. You are very welcome, and all the information of the commission is in the web page at IAU. In this term, the organizing committee was composed by these colleagues. As president, Sinobi Malkin. I was the vice president. Secretary was Laura Fernandez from Argentina. Past president Florian Seid. And the elected member were Laura Fernandez, David Salstein, and Jan Souchet from France. And the second term was Hadia Hassan Selim from Egypt, Xuanyen Jin, China, and Yolanta Nastula. And we also count on some non-voting representatives to important organizations for our commission, in particular IAG, Robert Henkelmann from Germany, IERS, Daniela Thaler, also from Germany, and from IEDS, Oleg Titov is also a representative. Well, all the details are given in the triennial report that appears in the web of the commission. We have there all the details, and in addition to that, usually the members of our commission also are participating in working groups outside of the commission, both in IAU, like in the International Celestial Reference Frame, for example, or TIME, and also in other organizations of relevance like IAG, GIGOS, etc., and also participating in the scientific organization of some meetings of interest. We reported some results in the Busan meeting, but probably the most important achievements of our commission was the approval of resolutions B1 about Bill BA and the challenges with the next generation of BIGOS, especially related with the protection of new observations bands, and a second resolution about the need of developing a new Earth rotation model that fulfills the current accuracies. Just to remember that the current precession and nutation models are more than almost 25 years old. Both resolutions are more or less explained in approximately plain language in an article published in March in 2022 in IAU Catalyst, so you can get there more details. Okay. There were two active working groups in this term, one related with improving theories and models of the Earth's rotation, led by Jose Fernández, who is here in the room, and there were some achievements like those that have here. There is some related proposal that was presented in the 2022 Unified Analysis Workshop, and that are available at the Zenodo website. And also there was a working group about the consistent realization of the terrestrial frame, celestial reference frame, and EOPs, because these three entities are highly connected. And it was chaired by Robert Henkelmann and also by Manuela Seitz from Zurich. Okay. And another issue was the preparation of a proposal about a IAU symposium that I will comment later, together with our colleagues of other IAU bodies, and it will finally be held next year in Argentina, but I will talk about this later. For the next term, after the elections, I will be the next president, and as vice president will be Jolanta Nastula. It's an error. So from Poland. It could be nice to be from Spain, but Poland is also okay, no problem. And we will keep, it was my mistake, sorry, Jolanta. And Sinobi Malkin will be the past president. And as new members, we have Tobias Nilsson from Sweden, Harald Schutz from Germany, and Mian Zhang from China. And we keep Laura Fernandez, David Salstein, and Jan Suchey. And as the usual goals of our commission is to stress the importance of our field for many parts of astronomy, geodesy, navigation, etc., and trying to join more colleagues, especially the younger ones. We see some problem with the we need to add young people to our committee, to our community. And from a scientific point of view, the most important thing is related to resolution B2 and has to do with the realization of such a resolution. So we should discuss the best way to update effectively in the short term the IAU precession and nutation models, and how to do that in a convenient way for the purposes of the resolutions. And in that sense, it is scheduled that we will create two working groups, one about theory, and another one about the prediction of Earth's orientation parameters. That will be the idea. And also, we aim to still cooperating with other IAU bodies, for example, in the next release of ICRF or whatever other things. With respect to the working groups, they are on move. We will give more details tomorrow in a business meeting of our commission, and they will be chaired by one of them, Jose Fernández, and as by President Chen Li Huang, and the other one by Jolanta Nastula and Jason. Okay. And next, I will give some, of course, one of the goals of the commission will be the successful meeting of the IAU's 401. I will give some basic information about the meeting. The meeting is entitled Advising Reference Systems, Ephemeris and Standards, with the subtitle From the Earth and the Moon to Solar System Bodies. And here appears all the co-chairs of the meeting, Felicita Arias, Flora Paganelli, Ryan Park, Susan Stewart, who is here, and also Laura Fernandez, who is our host in Argentina. Okay, well, it was a joint proposal of Commission A2, A3, X2, working group on time metrology, and working group on cartographic coordinates and rotational elements. And later we get the support of all IAU Division A bodies. For example, Chris Jacobs supported us, also Patrick Charlotte, and all of you. So thank you very much for that. Thank you very much. And also we got with the support of Division B and Division F. The symposium will be hosted at the National University of La Plata, in La Plata, close to Buenos Aires, in Argentina, by our colleague Laura Fernandez. Okay. More or less, the questions was that we detected a need to hold an IAU symposium on core topics of astrodynamics. There were different things, but such things were not considered in the last symposiums, or at least from our point of view. In fact, the last IAU meeting related with some core themes of the symposium was held almost 25 years ago in Washington. It was the colloquium towards models and constant for sub-microarc-second astrometry. Of course, other topics related with astrometry or with NEOS, etc., have been considered, but the focus is different. Our approach is considering both celestial and terrestrial frames, and also BLBA, and also EOPs, and also the motion of other bodies, and also the ephemeris of NEOS. So it is a different focus. Okay. Well, the proposal was prepared by the co-chairs, as I mentioned previously, and finally the meeting was approved. More or less, I will skip some details, but the scientific organizing committee is confirmed. Here we have the members: Chen-Li Huang, Yolanta Nastula, Oleg Titov, Manuela Seitz, Laura Fernandez, Agnes Fienga, Mitsuhiko Hosokawa, Dimitri Pavlov, Giovanni Balsecchi, and Catherine Hohenkerk. And we have basically some plenary talks, some invited talks, and contributed communications. And for the plenary talks, we have one about Earth rotation and reference frame by Harald Schultz, one about time by Patricia Tabella and Noel Dimarc. Felicita spoke about it later. And one about NEOS by Marco Micheli, that it is also of the room. Thank you, Marco. And another one by George Kaplan from USO. Okay. Well, the meeting is divided, is 1 week long, and is divided in 6 sessions. The first one is about Earth rotation, with the chairs Yolanta Nastula, Chen-Li Huang, and myself, and also with invited speakers confirmed: Christian Bissoir, Jose Ferrandiz, Justina Slivinska, and Pensu Oduan. The second one is about the terrestrial reference frames and their observations, and keeping its consistency. The chairs are Oleg, Manuela Seitz, and Laura Fernandez, and as speakers we have invited speakers, we have Aleta David, Xavier Colliux, Robert Heikelman, and Lucia McCallan. Third one is about reference frames and systems for the Moon and other solar system bodies. We have the chairs Agnes Fienga and Flora Paganelli, and as speakers Brent Archinal, Nicolas Gambou, Sergei Glioner, and Luca Porcelli. For time, as Felicita has mentioned, we have Mitsuhiko Hosokawa and Felicitas as chairs, and as invited speakers Josep Anchar, Tetsuya Ido, and Pascal Defrag. For ephemeris, there is a focus on the ephemeris of the NEOS. The chairs are Giovanni Balsecchi, Dimitri Pavlov, and Ryan Park. As invited speakers, we have Karen Mitch, Malgorzata, Koliskova, Federica Spoto, and Santanu Naidu. And the session about astronomical standards is chaired by Catherine Hohenker, Susanne Stewart, and as invited speakers we have Tony Wilmot, Sarah Bryan, and Detlev Angerman. And there will be also a round table, very interesting, to share the experience between the standardization with different international organizations. Okay. The meeting is in La Plata, close to Buenos Aires. The venue is at the National University of La Plata, in La Plata downtown. We have the help there about local organizing committee, led by Laura Fernandez, and it is more or less an old place. The Observatorio de La Plata goes back to the 19th century. We have some photos about the observatory and the cathedral in La Plata downtown. And as a final takeaway message, we have the International Astronomical Union Symposium number 401 from the 4 to the 9 August next year, La Plata in Buenos Aires. There will be IAU travel grants for symposium participation, and all the information is in the web page. In case of any doubt, you have my email or any contact. So I hope to see all of you there next year. The meeting is hybrid in case that you cannot attend in person. Finally, I would like to give the thanks to Daniel for the support. Thank you, Daniel.
Gives you additional time. So rendezvous next year then in the Southern Hemisphere again. And some other reports for the Commission will also be on the IAU webpage, the triennial report. Some other Commission did not make it. And the last report is for Commission A3. And maybe we'll have some discussion later.
Maybe, if there's time. Yeah. People want to hang around. Sweating slides. Oops. Okay, I'm going to give you a just very brief update of Commission A3. We're Commission A3 Fundamental Standards. I have served in the last triennium, and Jose Fernandez is going to be serving for the next triennium. So I'm very glad that he's taking over. Okay, so the mission for the Commission A3 is pretty straightforward. We are to maintain standards and communicate standards. We started, when I took this over, we decided to maintain a web presence where we are keeping standards lists. We're tracking emerging standards, things that we want to put up for discussion or possible updates. And we're evaluating these, making recommendations and updates, and we're also communicating, which we're doing well through the web presence. We're also enhancing links between the IAU, our IAU Commission, and other partners. There's some lists there of organizations, some within the IAU and some externally. We have representatives from those groups on our working groups or on our commission, and we communicate both ways. Okay. So our organizing committee coming in is listed here. We have Agnes Vienga taking vice president, so she will be training to take over in the following triennium. And we have some new organizing committee members there listed. And we have 108 commission members for standards. Our website lists our annual report and various standards list. One of the things we did was we took over the NSFA list. It used to be a working group, And it was willed over to us when NSFA concluded. So we're keeping that list of fundamental standards, and also CBE is the current best estimates. They're more derived standards. We also list standards organizations on our website. We track emerging standards, and we also list a change log. So any of the standards that have been updated, we list what they were, when they were changed, to keep them detailed. Here is our website, just where we keep all these things. You can see there the address at the top, and the links. This is how we have now organized through the last triennium. We did a reorganization of the former NSFA website so that it was better organized to find things. And this is what it looks like now. So these are the standards that we track and our update. For the next triennium, we have several lists of standards that are on the list of things to potentially update. Most of the updates come after there's been a mission to update these masses of solar system bodies. After post-mission analysis, we get better data, papers come out, and we are tracking which ones need to be updated. These are the list of things that will be updated in the next triennium. And we are proposing to have a working group to settle this, and these updates be made. They will be put on our website, and we'll send out a newsletter that says when they've been updated. I've also you've already heard me today talk about the lunar standards. One of the main activities of our commission this past 3 years has been to put up the resolutions for the lunar reference system. And we did that through a lot of international cooperation with the organizations listed there. We are also, as I said, going to suggest that we have a working group to update the current best estimates, but also we're going to suggest a working group for lunar standards specifically. Time standards, you've heard Felicitas speak on the redefinition of the SI second and continuous UTC. Those are things that we're tracking for the future and how they'll affect the other standards that we list. We also have, it's been suggested, and you heard the talk today about the updated value for the Earth's dynamical ellipticity. That's something that we're also tracking. And we've also had some feedback that we offer the standards in machine readable form. So that comment came in that we're tracking as well. Okay, so we have an email address that goes straight to our commission. So with changing leadership, it's always going to have the same email address. We actually have a Twitter account that was approved by the IAU. It hasn't had too much action, but it's there should we need it. On our website at the emerging standards page, there is a Google feedback form. So if you want to communicate with us that way to put in your ideas for standards or things we might want to be looking at, go ahead and find that feedback form there. I'll also mention that we're going to have a commission business meeting tomorrow at 11 o'clock in Pod C, which is in the main exhibit hall in the back corner. I think the white pods back there. So that's at 11 o'clock Tuesday, tomorrow, should you want to join us to talk about standards and other business matters. Okay, with that, I'm going to yield the rest of my time to David Soderblom, who is going to speak to you about a working group that would be under our working group, our commission that he's proposing.
Thank you. And now for something completely different.
Hit the green button.
This one for us and just is the pointer and this for
Ah,
the slides.
okay.
Yes.
Oh, okay. Got it. Thanks. So, who here in the room was born before 1958? Come on, raise it high. Come on, don't be ashamed. I was born a long time before then. Yeah. Okay, here's the deal. The current galactic coordinate system used dates back to 1958. And we've kind of learned a thing or two since then, at least we hope so. And there were some updates to 1985, even that is a long time ago, 40 years ago. So we know a lot more, and sometimes all that additional knowledge can add uncertainty, but sometimes we can improve things a lot. So the goal here is to create a revised, updated, improved galactic coordinate system that's suitable for modern times. And some of the questions that come up are how to define the galactic plane, which is probably one of the harder things. Precision versus accuracy. Can we improve on L2 and B2 significantly? And I think the answer is yes. Do we need it? Is it relevant? And I think the answer is yes. And can we also create a coordinate system based on the galactic center, not on the sun? So the essential parameters are the location of the galactic center and plane. Now, the galactic center, of course, is really well defined by Sag-A star, the black hole at the galactic center. So that's at the milliarc second level. But the galactic plane is another matter altogether because there's warps and other structures in the galaxy. And so you have to try to come up with some reference plane that deals with that. There's the distance of the sun from the galactic plane, and of course, the distance from the sun to the galactic center. And those are significantly better than they used to be. And then finally, there's the circular velocity of the sun with respect to the galactic center. So our strategy is to form a interdivisional working group based with this division, Division A, and Division H, which studies the galaxy. Look for community comment and involvement and get information, make recommendations, and finally come up with a resolution for 2027 in Rome for a revised galactic coordinate system. So these are the people who are currently involved in this, and I've established this by working through people I know, and they tell me who I should be talking to and so on. So one of the big reasons I'm here today is to get other input on people who should be involved, whether it's yourselves, please talk to me, and or people you can suggest who should be involved in this. And that's it, short and sweet.
Thanks for being in time. Are there any question, comments for the working group or the Commission on Standards? And oh, sorry.
Just a quick comment. I worked with David Gordon, and we measured the position of Sag-A star in the ICRF to, what was it, 0.5 milliarc second, something like that.
Yeah, it's quite impressive. It's so good. You can see the reflex motion of the sun orbiting the center of the galaxy. I love that. You can see a change in the position, in other words, a proper motion of an apparent proper motion of the object.
If there is no other urgent question, we can leave it for the gala dinner, etc. Because we wanted to have some time for the discussion that we didn't have in the previous session about the lunar standards, and maybe we can take a few minutes, up to 10 minutes, and we'll also see if people online can join. So Patrick, Charlot, you want to? You have a meeting that will start in 5 minutes, not before in this room. Okay. So. Yeah, so we were too long this afternoon. In any case, and the resolution will also be discussed again on the business meeting on Wednesday.
we can have some conversation about lunar standards in the business meeting for fundamental standards tomorrow at 11 o'clock in Pod C. We can talk there as well.
Okay, so invitation Pod C in the exhibition hall tomorrow at 11, and on Wednesday afternoon, I think it's about the resolution stuff. And so we leave the room then for. This is well, it's not the end of Division A, it's the end of my presidency as president of Division A. And it will be Bonnie Steve that will take the lead next. And yeah, it was happy to organize this, and thank you for being member of Division A. And if I have maybe a last message, and I repeat it again, everything is fine. It's Division A, nice commission working group, functional working groups, but we don't have many candidates for the PhD prize. So if I have a last message to give, I don't know how to improve that, but that should be something we can improve in Division A in globally, I would say. So thank you again. And a nice continuation for the General Assembly. Désolé.